of you who are arriving, a quick installation check of the things that we want to make sure you all have. You should be able to type at a terminal the command IPython notebook, and you should get something like this come up. You should get a message like that with a URL on localhost. It might or might not open a browser, but if you go to that URL, you should see a page like this. If that is not the case for you, then you want to install EPD, the Enthought Python distribution. It would be the simplest way to get you going. And we do have copies of the EPD free installer available on USB sticks and CD-ROMs in the front of the room. So just grab one of those and do the installation. We have the installers for all platforms. We would greatly appreciate, EPD free is free for both commercial and academic use, but if you do the installation of EPD free, we'd really appreciate it if you could go over and at least register yourself, because that is basically the download. And what we're doing is simply bypassing their download page, because they told us at the conference that we should not rely on the network for downloads, because it could perhaps not be up and running or not support 80 people simultaneously doing a large download. But we'd appreciate it if you would at least basically provide the first step of the process if you use the downloads that we're giving you. Enthought has been very, very supportive of the project over the years, and we would like to reciprocate that by acknowledging that they're letting us use this and having you guys do the same thing that you would have done to do the download. In addition to EPD, at this URL, there's a zip file that contains the class materials. Those are also on the USB sticks and the CD-ROMs, but because this is a small download, you can probably get it from the net quicker than passing a USB stick around. That's a zip file that has the 3 folders other than the EPD folder on the USB sticks and CD-ROMs. And it's 1 minute till 9. I'm wondering if we should just start in a really timely fashion, because we have a lot of ground to cover. Should we? What's that? It's 9 o'clock. Okay, I don't see anyone walking through the door, so I am going to start with the head count that we have. Okay, so we're going to officially start now the tutorial, and first I'd like to welcome you all. On behalf of the IPython team, we're really thrilled to see the interest this tutorial has had. We have 64 people registered, which means it's going to be cozy for the next 3 hours. It may not be possible to have an empty chair between every pair of persons, between every 2 people, because at the end the room might fill up. But we hope it'll be a very productive and interesting session. I'm going to run officially the installation instructions that I've been giving over and over, and that we've been giving over and over, so that everyone actually has a chance to see them. What we want to make sure is that you can run the following, that you can run the IPython command and get something to start, and furthermore, that you can run the command IPython notebook, and that if you run that command, you get a message like this that points you to a URL such as this, and that if you go and visit that URL, you see a page such as this, and that you can click on the button that says New Notebook, and it will open something roughly like this. It won't look identical to this. You may have a slightly older version, but it will look very similar to this. If that is not the case, the simplest solution is to install the Enthought Python distribution. The free download of Enthought is called EPD free. You can find it here, but we have copies on several USB sticks that are making the rounds, as well as a bunch of CD-ROMs, so that you can download the installer, and we have copies of the Mac, Windows, and Linux installers of EPD there. What I would like to do is have whoever doesn't have this up and running yet, try to do it during the next 15 minutes while I give a short introduction with slides, because the rest of the session, we will want you to be working interactively with us. And if you have any problems, please raise your hand. We have 4 more, 2 other instructors and 2 TAs who will come and help you out, sort out any installation glitches you may have in the next 15 minutes. And so hopefully, by the end of the intro period, we will all be at the same spot and everyone will be able to work together. During the day, during the tutorial, we want you guys to interrupt us. This is meant to be very interactive. And if you have any problems where you don't want to interrupt the speaker, but you have a little bit of a glitch, raise your hand and call out one of the others. We will have 1 speaker at a time, and we have 2 TAs and 2 more speakers. Any of us will come to you and try to give you a hand, okay? So, as I said, thanks everyone for coming. So we want to start by telling you a little bit about, giving you a quick overview of what the IPython project is. Oops. Can everyone hear me correctly, and is the sound okay for the recording? Okay, perfect. So, my name is Fernando. I work at UC Berkeley, and my co-conspirators in crime in the IPython project, BrianE.Granger, who works at Cal Poly San Luis Obispo, and MinRagan-Kelley, who is a grad student also at UC Berkeley, would like to tell you basically how to use IPython to be as productive as possible when you work in the Python language. And so, why did we start IPython? What is the motivation behind the project? The I in IPython is for interactive. And the reason is we're all 3 scientists. Brian and I met in grad school in physics when we were doing our PhDs in physics, and Min was also a physics student of Brian's back in Santa Clara. And a common thread in scientific computing is that when you use computers to work on scientific problems, you don't know what you're doing in advance. You don't have a well-specified set of requirements. What you do have is data, algorithms, libraries. You play with a problem, you plot some data, you have an idea, you try something else. And so it is essential for effective scientific computing to have tools that are very fluid and that allow you to have a very exploratory workflow. We don't come in scientific computing, or rarely do we come to a problem where we have a well-defined set of specifications that we have to implement, and at the end of which the job is done. That is just not the case. And as it turns out, Python is a great base for an interactive computing environment. The language is very lightweight. You don't have to declare types. You can execute code immediately. It has great introspection facilities. However, it's just a starting point. It's just a base. If you type Python, the prompt you get, and you get the triple greater prompt, if you try to look at your files and you say you type ls, which would be a natural thing to want to look at your files before you do anything, that doesn't work. If you have a module imported and you ask about what is it, and you think, oh, maybe the question mark would tell me, that doesn't work. If you try to execute a file and you give it a path with the tilde syntax, it doesn't find it. If you give it the full path and the file happens to have an error, the error messages are not terribly informative. You have a lot of black text on your terminal that isn't very well delineated and demarcated. I think we can do a lot better than this. If we're going to spend all of our day working interactively, that is just not sufficient. And so IPython tries to do better, and IPython tries to give you tools that are a little bit nicer to work with. So if you type ls, you can use tildes. It will give you it will tell you about your files. If you ask for object details with the question mark, about, for example, if you type OS question mark, it will tell you what is OS. OS is a module. This is its base class. It will give you its string form, where was it loaded, what is the file where it's defined, and what is its stock string, so that you can immediately query your objects. If you say, I would like to know more about an object, and you use 2 question marks, IPython will dig deeper. Python has a lot of introspection capability, so we dig deeper, and we give you the source code, and we syntax highlight it for you, so that you can see the details about your objects immediately, without having to go to some other place, without having to find the files. If you run a file that has an error, this is what a traceback looks like. When you're debugging, this, I think, is a much nicer way of, in one glance, understanding what's going on than this. I hope you will all agree that when you look at something like this, it's much easier to spot exactly what is going on, what does the stack look like. You can even ask for local variables to be printed in the stack trace so that it's easier to quickly figure out what is going on. So this is what IPython looked like for a number of years while working at the terminal. And we built a terminal client that has a fair amount of useful bells and whistles. And that terminal client eventually added support for interactive visualization, because in scientific work, we need to plot data all the time. It turns out that by default in Python, if you open a GUI window, the terminal blocks. So we added support for that not to be the case, so that you could have multiple windows, plot windows open. These windows come from the Matplotlib plotting library. We have one of the core Matplotlib developers in attendance today with us. Matplotlib supports plotting windows in any of a number of GUI toolkits. You can have your GUI windows be Qt windows, GTK, WX, TK, or native OS X windows. And IPython manages to give you non-blocking behavior of the plotting windows with any of those toolkits. That took some work to get going. After we built that, later on we developed a richer client. So IPython now also has a second terminal, a second client, which allows you also to type code. It feels like a terminal, but it is a graphical console written using the Qt GUI toolkit. So this is a client which feels like a terminal. It tries to have the very lightweight fluidity. When you open it, it looks like a white terminal with a black, like a terminal with a white background. But if you run a code that produces figures, the figures are inlined. If you type multiple lines of code, the text is syntax highlighted. And furthermore, you can edit with the up arrows back and forth in a multi-line block, something which you cannot do in a terminal, for example, simply because those are the limitations of the read line, of how a read line terminal works. It has graphical tooltips. It has many features that are simply not possible in a terminal. And yet, it retains the very lightweight feel of a terminal. And what this is doing is communicating from the Qt process over the network to a kernel executing your Python code. So we've basically split up the terminal-based IPython. This guy has been split up into two processes. One process executes the code, and another process communicates using the 0MQ networking library with the Qt client. Once we had that architecture for communication between a client and a back-end process of an IPython kernel, it became possible to build more clients. So we had a meeting with the Microsoft folks, and we explained to them what the design of the architecture was, and then they went ahead. Dino Wieland did a phenomenal job in implementing an IPython console that runs inside of Microsoft Visual Studio 2010. So for those of you who are Windows developers, the Python tools for Visual Studio include this, and obviously this is not written in Python. I imagine that Visual Studio is written either in C++ or in C#, or I don't know exactly what they write with, but the point is, this is not a Python program, yet all they had to do was speak our protocol. We explained what the protocol was. It's documented in our documentation, the specification of what the messages have to look like, and once they had the communication going, then they could put a full-blown IPython inside of Visual Studio. And finally, something that you will see a lot more of later is we have recently released, in the latest 0.12 release that came out right before Christmas last year, we have developed a web-based notebook, which is a Python environment that has cells where you type. These cells that have the IPython-looking prompts are cells where you type Python code and it executes, and it's the real IPython. We're actually talking to the exact same kernel as before, the exact same kernel that the Qt console or the text terminal is talking to. This guy is talking to the same thing, mediated via a Tornado web server that basically translates the 0MQ network traffic into WebSocket traffic. So you do need a fairly modern web browser for this to work, but as long as you have Chrome, Safari, or modern Firefox, it works fine. But the advantage of this environment, and you'll see a lot more of this in a minute, is that in addition to executing code, you can also type text, and the text can have rich formatting, it can have hypertext links, it can have mathematics, which for us as scientists is very important. You can also have plots inline, you can embed rich media, you can have videos embedded, and these files can be saved as documents. So now what you have are computational documents where you can do your work, write your notes, keep your figures, and save them, version control them, share them with colleagues, put them on GitHub, et cetera, et cetera. We're very excited about this. For us as scientists, this has a lot of very important uses, but it's important to say that even though IPython is mostly developed by scientists, we've gone to great lengths not to create any dependencies on scientific tools. So if you're in a different field, if you don't need the mathematics or the data visualization, those are not dependencies. IPython runs perfectly okay, the web notebook runs perfectly okay without Matplotlib for plots. It cooperates with Matplotlib for the visualization if you need that, but it doesn't need it to operate. And finally, we've extended the same architecture also for very high-level parallel computing also using 0MQ, IPython tries to let you make a very natural transition from interactive exploration of a problem on a single machine to extending execution to either a multi-core box, a local cluster, or even a cloud computing environment on Amazon, for example, by abstracting out the kernels that we were talking about a minute ago. You can run n of them, and we call them in that context IPython engines. Basically, they have a little bit of additional transport capabilities for data, and all of these engines talk to an object called an IPython controller, and this group of processes put together, one controller and n engines, constitute what we call an IPython cluster, which you can manipulate interactively, and all of this is persistent. You start your cluster, and that cluster could be running on your multi-core laptop or on EC2, and then you connect to it and disconnect from it with clients. These clients are precisely the interactive environments where you create an object that proxies the data that is in here and allows you to send data to these things, retrieve data from them, create tasks for execution. It basically gives you very high-level parallel execution while decoupling the client work that you have here from the persistence of the cluster. And we will see more of this in the third hour of the tutorial in detail, but the basic idea is that you can connect to your cluster, retrieve some data, sever this connection. You could go home, for example, later at home, connect again, see how things are going, pick up some more data for visualization. You could call a colleague and say, hey, I want you to connect at the same time, and I want you to look at these two pieces of data while the cluster hasn't been shut down. Your colleague can also pull data to look at it locally. And so we've basically tried to make a very natural transition from the interactive single-person terminal flow to a collaborative web environment to full-blown parallel computing with the same set of tools and the same set of abstractions. A very quick history of how we got here. I started IPython in November, around the end of 2001. I promised myself this will be just a quick afternoon hack, 11 years and counting. The first version of IPython was actually a Python startup file that was 250 lines of code. Later on, I found out about IPP and LazyPython, two separate enhancements to interactive consoles in Python from two different authors. And I basically asked them if they wanted to join forces. If they wanted to join forces with me. They said they had no time for it, but that they would be happy to let me use their code. And so the merger of these three things became the first IPython. In 2002, John Hunter sent me some patches to improve the GNU plot support that we had at the time in IPython. I was at the time busy finishing my PhD, so I had to ignore them, and it's one of the best decisions I've ever made, because by ignoring John, he went out and wrote matplotlib, and now we have a spectacular plotting library. In 2004, Brian and I met after a SciPy conference, and we were friends back from grad school, and we started talking about the merger of the interactive ideas with some early parallel computing prototype code that Brian had. And Min, who was his student at the time, did his senior thesis as the first implementation of these parallel ideas, but using a twisted backend. Then between 2005 and 2009, we had sort of a slower period with a few new features came in, not too much major work was done. We did a lot of thinking on many problems, though. And towards the end, we did a very large refactoring of the project that turned out to be very important, because in 2010, we discovered the 0MQ library, and it looked like exactly what we were looking for. It seemed like the abstractions it exposed were exactly what we wanted, and Brian jumped on it and in 2 days wrote the first version of the PyZMQ bindings, put them up on GitHub using Python, and basically, the project really took off from there. We moved to Git and GitHub, which has been absolutely fantastic for us. It has really made a huge difference in our development. With Enthought support, we built the Qt console. The parallel code that Min had written on top of Twisted, he rewrote it in one of the most amazing feats of development I've ever seen. He rewrote it on top of 0MQ in a couple of months all by himself. And Thomas Kloiver joined the project and did a Python 3 port. Then finally, last year, we developed and deployed the first version of the web notebook, something that we had wanted for a long time. Here is a list of the people who are working currently on the project. The names in bold are the people who belong sort of to the core committers team, even though GitHub really democratizes that significantly, and there isn't a major difference between a core committer and somebody who's contributing from their own fork on GitHub. The names in blue are people who are in the room here. So Paul Ivanov is in the back. He's standing there, and you can talk to him later. He's also a grad student at Berkeley. And Brian and Min will be speaking later. The important point is that we do have by now over 140 authors in the commit log. So it is a project that has a reasonable level of activity. The code base is a little over 100,000 lines of code, so IPython is not a teeny, lightweight project anymore. It's not just a shell anymore. So my afternoon hack of 250 lines of code has certainly ballooned, but we think it has ballooned for good reasons. It's useful to many important projects. This is a list of scientific projects that use IPython, and when I say use, I mean they use it as a library, as a component of the project, not simply that there are people at these places who use IPython as a shell. That by now, probably anyone in science who uses Python uses IPython. And there are also non-scientific projects that in one way or another have extended or integrated IPython into their flow. We've received support from a number of people that we appreciate a lot, in particular Enthought, as we said. They've been great. They've supported the project since its inception in many ways, and we really appreciate that. And we've also had some official, corporate funding and some government funding. Right now, we actually do have some stable funding from the Department of Defense, and we continue to look for federal funding. We're all in academia, so we continue to sort of to play the absolutely dreadful funding game of academia. So to summarize what we've seen so far, so that you guys have kind of a very brief idea of what IPython is, and I'm coming right on time to the end of my time here, IPython gives you, first of all, a better shell. If nothing else, the basic shell has no dependencies whatsoever beyond the standard library. So all of the other fancy stuff that you've seen, if you're in a server somewhere that has no GUI toolkits, nothing else, just the standard library, IPython will run. The other things may not, but the basic improved shell will run. On top of that, we have this rich toolkit with a terminal, with terminal clients, GUI client, and web notebook, and finally, our high-level interactive parallel computing interfaces. This is the website for the project and our developer site. We would love to have you contribute as developers now that the project has a web component, Qt GUI code, terminal-based code, networking code, parallel code. There's a little bit of everything in the project, which means we need people with different skill sets. We are not web developers ourselves. We would love it if some of you who have those skills come on the project and help. There's plenty to do on the web notebook, as you will see later, and there's plenty of exciting and interesting stuff to do there. So, and those are not our core competencies. So please, join us, and now we are going to switch gears into trying to all work interactively. So I want to do a spot installation check. How is everyone doing with the install instructions that we gave? Does anyone still have a problem? If you do, please raise your hands, and the 4 of them will come and give you a hand, because it is really important that over the next few hours, you can try to work with us. And there's installation CDs in the front. So I'm going to wait for a minute or two to give people a chance to catch up on installation. If you're done with the USB sticks, please pass them to the front. We had 5 of them. We hope to have 5 of them by the end of the tutorial. David, question?
What's the compatibility with
Safari? It should. Min, can you?
I think there's a WebSocket issue if you have the very latest Tornado and O.12 IPython on current Safari. The latest Tornado removed support for the version of WebSockets or instead of default, change the default.
Ouch.
Tornado 2.1, it will work. The notebook O.12 or Tornado, current Tornado with master IPython.
So what should David do? Should he?
It works in Firefox.
Yeah, it works in everything but Safari. If you really want Safari, you use install Tornado.
Any USB sticks from these ones right here.
And I can come as well. We'll take a couple minutes. We do want everyone to be able to use the tools during the tutorial. So I imagine that many of you do. So a quick show of hands. Who here in the room has used at least the terminal version of IPython so far? Okay, so most of you. Who hasn't? ever used it? Okay, a few of you have never used it. And since we said that this would be an in-depth tutorial, but starting from the beginning, we are going to cover the early parts of IPython. So I'm going to spend the next 35 minutes or so covering the terminal-only part, the terminal and the Qt console. If for some of you, the Qt console part doesn't work, then simply continue working with the terminal, because the Qt console and the terminal feel fairly similar, and the problem is that you need to do the Qt installation, and that's a huge download that we didn't want to deal with right now. So you can see if the notebook works, you have all the dependencies for the Qt console, and you can install Qt later if we try to download 60 copies of PyQt right now, it'll just take forever. So simply, if the Qt console doesn't work, continue working in the terminal, and that is fine. But for now, when you start IPython, and I'm going to start it with light background colors, because this is a light background terminal, this is what you get. So IPython tries to be, at first, just a better Python shell. So anything you type which is valid Python that you would type at the triple graded prompt shell should work in IPython. In addition, it gives you a few other things. And first of all, you should heed the little information that is there. So if you're new to IPython, try following that. It says, just type question mark. If you type question mark, IPython will show you a help screen that gives you a short intro to the basic ideas and the most important things that are different from the Python shell. Obviously, anything that works in the shell works in IPython. We try to tell you a little bit about what are the most useful things you should know about IPython when you get started. Now, in addition to the basic intro, there's a cheat sheet. So if you type quick ref, there's a quick reference card, which is basically a summary of the basic, just a cheat sheet summarizing all the special syntaxes and the various things that IPython does for you. And it would be worth your while to spend 5 minutes reading the question mark summary and the quick ref card, because there's a lot of little tips and tricks in there that will save you lots and lots of typing. As Brian likes to joke, much of the success of IPython has been thanks to encoding all of my OCD into typing as little as possible. And so there's lots and lots of tricks in there to try to make you productive with as little typing as possible. So please have a look at those things, because we won't have time to cover all of these in detail. What we'll try to do is show you some of these and explain some of the more complex parts of it. Many of these things are just, you read them, you understand how they work, and you just keep going. So one of the parts of IPython where most work has gone into is into taking advantage of the introspection capabilities of the language to let you explore your objects very easily. And that is done via the tab key. The tab key is the key that you will wear out in your keyboard with IPython. If I type import and I type tab, let me just go back up to the top of my screen. If I type import and I type tab, IPython will complete. But if I tap complete on NUM, it also types complete packages. If I say from NumPy import that, it also tab completes what I can import, and it hasn't imported NumPy itself. It is only introspecting into the package. So the tab key tries to introspect into many, many things. If I say exec file scratch, it actually completes there. And it completes file names as well. If I say A is hello PyCon, and I tab complete on A, it also tab completes on objects. So the tab completion mechanism in IPython applies to namespaces, files, objects, just about anything you can think of. And furthermore, it's extensible. You can define your own completers that do things like complete inside of dictionary keys, for example. That does not work by default, because accessing members of objects, doing internal object access can have side effects, and we don't want to enable that by default, but you can turn that on. In fact, we have an extension that does that for you. You just have to turn it on yourself. And you can define custom tab completers. There's a project in Europe that defined a tab completer that actually sends remote requests to a neutron spectrometer facility, and actually it tab completes on data from the hardware facility in real time. So you can define tab completers that do all kinds of exotic things. Okay? So that is the first part of the introspection capabilities of IPython. The other part is the business with the question marks that I showed before. If, say, I import code from the standard library, and I would encourage you to type along with me if you want, because all of this is about building muscle memory. You want to know, and if you get confused, for example, if you do this, you will get information about the code module. If you do double question mark, you will get a pager. But it's important that you know how to get out of the pager. Those of you who are old Unix hands may know right away how to get out of it. If you don't, you get out of the pager with Q. We use the less pager. And so when you use double question mark, what IPython tries to do is actually dig into the object and find its source code and show it to you. And you can do that at the module level, but you can also do that at the class level. So let's see, I dig into one of the classes defined in the code module. And I do this, then it will show me the code only for that object, okay? We even if I define a function interactively like this, then we even show you not only its definition, but we can even show you its source code. It turns out it's not trivial to show the source code of an interactively defined function. If you try that in plain Python, that doesn't work. It works because we've created, we've played tricks. But basically, we try to do everything possible to help you as much as we can with your objects while working interactively, even including things that by default are not meant to be sort of possible in Python itself. So, as I said before, you should be able to type ls in IPython and have that work. You should be able to type cd in IPython and have that work. Okay? The idea is we provide a blend of the facilities of the shell and the facilities of the language to try to make interactive workflows very efficient. Now, obviously, cd and cd dash and ls are not valid Python syntax, right? What is cd? If we do cd, we have to change the working directory of the Python interpreter itself. We actually have to call internal Python functions to do that. So how would I find out what cd is? cd question mark. And so if I ask cd question mark, it tells me what cd is. And it tells me at the top that cd is something called a magic function. So in IPython, we have a concept called magic functions, which are basically commands that live in a parallel namespace to the main Python namespace, so that you can execute things to control the shell, to do a number of things on top of the basic syntax of the language itself. And magic functions are called like command line calls. You don't have to type parentheses, you don't have to put quotes around strings. The reason for choosing that was precisely because interactive typing, parentheses are a bit of a burden, quotes are a bit of a burden, so we try to make it more shell-like. But we disambiguate magic functions from the default Python syntax by allowing you to prepend a % sign into these magic functions. So I didn't, as you noticed, I didn't type %cd, I just typed c, yes.
We're going to interrupt you because
Yes.
about, I don't know, half this section here can't see anything you're typing.
Really?
To get to the bottom of the
Okay,
page.
so I'm going to cut my terminal in half maybe, or
Well, either that or if we can move the podium back.
let's try to do that without. Does that help? Everyone? We'll move it until I fall. Actually, you've made it very interesting for the speakers now. So, this may get funny. So, as you noticed, I didn't put a % before the cd command. Now, what happens if I say cd is equal to 1, 2, 3? If I now type cd, it is 1, 2, 3. Our policy in IPython is the language comes first. So if there is a variable that has that name, we allow that code to execute just like it would execute in plain Python. Now, in that case, you do have to disambiguate with the % sign. But if there isn't, the moment you delete the Python variable, then cd works again the way it worked before, okay? And so the magic system is extremely useful. You can effectively define entire libraries of control commands for specialized work that live on top of a normal Python shell. And so if you type simply magic, you will get a short explanation of the magic system, as well as a complete list of all the magics available with their docstrings, a very, very long list. This is pretty long. I'm not going to go through all of it. It's 2,000 lines of text, okay? But at the bottom, you have a summary of all the magics given by the ls magic function. ls magic is ls for magics. That will tell you which magics are currently available. You can define your own magics. We'll see in a minute how when we get to configuration. So this is one of the most useful parts of IPython because it lets you build customized commands that fit your workflow and which live completely separate from the main Python namespace. So we already saw the CD magic. There's many, many more. As I said, when you type ls magic, you see what all of them are. And there are some that are really useful while working interactively. One of them is the history magic. Since you're working at the terminal, when you're working at the terminal, the typical workflow is to use IPython for lightweight exploration and an editor to write real code. None of us writes more than 3 or 4 line snippet functions in IPython itself. We write all of our code in an editor, but often you do something at the terminal that may be useful. If you want to paste it later, you can type history, and you can see all of your history right here, and then copy and paste it. In addition to seeing your history, you can log your history as you go. So IPython has a log start command. It has a set of logging commands. The main one is log start to start logging. So if you type log start question mark, it will tell you how to start logging. You can log with timestamps. You can log the raw input that you type, or IPython can transform the magic syntax into valid Python so that the end file is valid Python syntax. You can actually log all of the outputs that are printed. Obviously, output isn't valid Python syntax in general, so that will be prepended by comment markers. But you can basically have a little text file that is a log of your session, and you can start logging after the fact. So if I type log start pycon.py and say with timestamps and output, then it begins auto-logging, and it tells me what commands I put in, and then if I cat pycon.py, this is the file. So it actually logs retroactively from the beginning of my session, and from now, because it has my input history, and from now on, it also logs my outputs here. It also logs my outputs as well from now on. It doesn't log outputs retroactively, but it logs outputs from now on, but it does log input retroactively. All of your history for all of your sessions is saved in SQLite databases, and we'll see later where those files are. They're in a place called your profile directory. So you can always retrieve the history from anything, and even if you're running multiple IPython sessions in parallel at the same time in different terminals, they write to different tables in the SQLite database, so they never clobber each other. That work was done last year by Thomas Kloiber, one of our new developers, who's really been a spectacular find for the project. So let me see where I am. Okay, so you guys should have, from the files that you downloaded, you should have the file called simple script in there. The file simple script is just this. Just a very simple file that it defines 2 functions, a couple variables, and it prints something. How do we normally work when we're confined to IPython? If we don't have the notebook, if we can't do real fancy multi-line editing like we can in the Qt console, my regular workflow and that of most other Python developers is basically to say, I am going to work half in a terminal and half in an editor. Pick your editor of choice. I have my editor here, Emacs, and here I have my terminal. And what I do is I want to run a script, so I run it. And I simply run the script with the run command. Run is, obviously, if we want to find out what run is, what do? We ask run. It runs the name file inside IPython as a program, okay? Run is not import star, okay? I'm going to explain carefully how run operates, because run is not from script import star. Run is actually exec file on steroids and with lots of control over the namespace, over what happens in the namespaces. So what happens when you run your programs is that this code executes in a namespace, and we go to great lengths to make your program believe that it's running in an empty Python process. The only thing that is really different is that any part of global state that leaks from the Python interpreter that we can't prevent from leaking may be visible. Some of that leakage is actually beneficial. The fact that modules that have been previously imported don't get re-imported means that if you have modules whose import is expensive, then running a script over and over and over doesn't force them to be re-imported. So if, say, there are some, for example, we use in scientific computing some visualization libraries whose import by itself, on modern hardware it's not as bad, but it used to be on the order of a minute. I remember ITK took about a minute just to import. Flat out CPU with a hot disk cache, import ITK took a minute. Well, I don't want to run, if I'm running a small script that uses ITK, I don't want to wait a minute every time I make a change just for the imports. But if I rerun it inside of IPython, cached modules are cached in sys.modules, and so the script itself, those imports won't get re-executed. Now, that may be bad. If you actually need to reload an extension module, you'll basically have to exit IPython and restart it. Now, if you do that, by the way, if you exit IPython and restart it, you will notice that the up arrow key works. Basically, we save your history up to that point so that if you quit the session and start it again, the history is preserved just where you left off. And that's precisely to make frequent stop and restart less inconvenient, okay? So what happens when you run the script? If you run the script, let's ask what the y variable is. In my namespace, there is no y variable. The script at the bottom defines y to be 4. If I run the script, now y is 4. So what happens is the script is run in an empty namespace, so it feels like it's just running at the command line. The reason for that is so that anything you develop in IPython, you should be able later to run it outside of IPython, and it should run the same thing. So if you put that later in a cron job, if you put it later in some other environment, you give it to a colleague who doesn't use IPython, it shouldn't all of a sudden stop working because you were using IPython while you were working. We really try hard for that not to be the case. But after you've executed your code, you want to play with the data. Basically, you run something, a bunch of things get defined, you want to plot them, you want to print them, you want to see what's going on. That kind of iterative cycle is what run tries to enable. So anything that is defined in the script is now valid. So now I can type, I can define that function, which simply does integer division. So we get the usual semantics of integer division. But you can, if you need, you can actually say, I want my script to, for example, let's imagine that we had a variable interactively defined called z, which is 100, and that we wanted to do this. Obviously, if I run that, it will produce a name error, right? But you can say, I want this script to run as if it was executed in my interactive namespace, literally, as if it was, if I was typing those lines right here, well, all you have to do is say run in my interactive namespace, and then it will get run. Instead of being run in an empty namespace, it'll get run in your current namespace. The run command has other facilities. If you ask, run is kind of our main workhorse, so I'm going to explain a little bit more about it. Run allows you to run a program under the control of the profiler with run-p. You can run it with timing with run-t. You can run it, and -n doesn't set name to main. You've seen many programs actually define their variables at the top, and then they have a part where they say if name equals main, and then this part is the main section, so that you can sort of separate the script part from the library definition part for import purposes. By default, run sets name to main, so the bottom part is executed. But if you don't want that to be the case, because you only want to load the definitions, then you can say run-n, and name is not set to main, so it is as if you were importing it, but it's not import start. The code gets re-executed, so you don't have to do reloads, okay? If you say run-t, the program is timed. This is a trivial code, obviously, so there's no CPU time to consume, but if your program was doing something significant, it would show you the timings. If you run-p, it actually runs it under the control of the Python profiler and returns the profiler results for you. So these are all things that the standard library has already. We just make them really easy to access, so you don't have to remember what the profiler module API is. You just say run-p, and you're done. Okay? Now, if you're doing timing, and you can also run it under the control of the debugger. So there, it starts the debugger, and you actually then can say continue, continue, and it will execute. This is not quite a standard debugger, though. As you see, each frame of the debugger is nicely syntax highlighted. That's not what the default PDB does, and tab completion and all the other features of IPython work. As you see, the name here says IPDB. So this is a slightly enhanced subclass of the Python standard PDB debugger that adds some of the IPython goodies on top of PDB. Now, what happens if we have a bug? What happens if I have a bug? If I call my script and there is a bug in it, obviously I get a traceback, as we said. We get a much nicer traceback than you get by default. You can actually change the exception reporting mode. There is a magic called X mode that lets you change the exception reporting mode. And there's 3 modes for it: plain, context, and verbose. Context is the default, which produces these kinds of tracebacks. Plain basically looks very similar to the plain Python traceback, just with coloring, but the frames and the stack printouts. The reason is that this is valid doc test. This is a valid doc test traceback, whereas our fancy ones are not valid doc test tracebacks. And the fancy one, verbose, actually prints, in addition, it prints local variables at all the frames and all the call points. Now, this is not the default because these things potentially may be expensive to compute. And you may have objects whose representation is very big, so we don't want to enable that by default because it may just be a little too much. But it's important to know, and you just toggle these by calling the X mode exception reporting mode, okay? So now we are going to briefly switch to the Qt console and then to see how we configure IPython. Yes, Titus? It better. Does it not? If not, open a ticket for it. It better. If there's nothing about it which is specific. There's nothing about it which is specific to the terminal, so it should. There are a few things that don't work in the notebook, but that is not one of them. And we try to keep the number of things that don't work in the notebook ideally to 0. The big remaining bug we have, or kind of missing feature, is that raw input doesn't work in the notebook because we haven't transported the socket. But we know how to do it. It just hasn't been done. It's just a matter of time. Min is a slacker. We only have like 35 outstanding PRs from him. He's really, really slouching off. So now I am going to switch to the Qt console, but as I said, this is for illustration purposes. If you don't have Qt installed and it doesn't run for you, don't despair. Just keep using the terminal. Most things work the same. I just want to show you how the console works. So you start the Qt console with IPython Qt console, and I will actually start this one with plotting support, just to show for those of you who may be interested in visualization, with the inline plot support. So if I start the Qt console and I say, use the PyLab, load the Matplotlib plotting facilities, and turn on inline figures, this is what happens. I get something that looks like a console, okay? And I'm going to make my fonts. Tell me in the back when I can stop making the font bigger. I want everyone to see, but I don't want to make it absurdly big. Is that good enough, or should I go one more? One more. Is that enough? Okay. So this, as you see, it kind of looks like a terminal, right? And I can type ls, and I can type magic, and the same thing happens, and I get something that feels very, very similar to a terminal, except that you start seeing different things. Look, GUI call tips, right? That can't happen in a terminal, right? The ability to get inline figures. You can say, oh, I would like to restart my kernel. And it asks me, are you sure? Yes, and it restarts the kernel, but it doesn't close the window. It simply kills the kernel process and gives me a new kernel. I can do I can then go back and do multi-line editing. This can't be done in a normal terminal because readline doesn't let us move the cursor up or down, only left or right. But in a GUI, and the keywords are properly syntax highlighted. You can theme, this is the default theme, but you can theme it with any theme that Pigments supports. So you can have a dark background, you can theme. Pigments out of the box supports like 10 or 12 different color themes, and you can write your own if you want. It's just a bit of CSS, okay? So basically what we tried to achieve with the console was the fluidity and the kind of lightweightness of a terminal, but with certain things that really are annoying about a terminal, like the inability to see your figures right there or the inability to do multi-line editing. Some of those things we tried to solve. And you can save a session, you can copy and paste, and you can do intelligent things such as if you do this, you can either copy or copy the raw text. The difference is that if you say copy, let me open an editor real quick to show. Oh, I have one open here. If I paste in here, as you see, it removed, I highlighted, the prompts were highlighted, and it removed the prompts. If you copy and say copy raw text, then it does copy everything, which may be useful if you're writing, say, a tutorial and you want to show the whole thing. But if you're trying to copy code that you typed a multi-line cell, you just want to strip out all of that. All of those things are just impossible to do in a terminal. So we think, and the console can be very, very useful in many contexts. In particular, you'll see how it plays with the notebook, in that this console is capable of talking to the same kernel that a notebook is talking to simultaneously. So the limitation of the notebook that I just brought up when talking to Titus about the notebook not supporting raw input, the console does support raw input. If I say x equals raw input, enter x, x is handling raw input is supported, even though raw input is actually happening in a different process. But we're forwarding the standard input of the kernel over 0MQ into the Qt GUI. Because that hasn't been implemented for the web notebook, then connecting a Qt console to a web notebook, to the kernel of a web notebook, basically lets you solve that problem. And doing things like interactive debugging that you can do, that the notebook currently doesn't support, can be done via the Qt console. Okay? So what are the things can we do in IPython? So ls, for example, is already defined. What is ls? ls is what we call a system alias. Aliases are yet another namespace, which is basically much simpler than magics. They're simply short names for system commands. So ls is simply an alias for ls-f-caller. You can define your own aliases with the %alias magic. So, but what if you want to execute a system command that you hadn't defined an alias for? And we predefined a few for you, but you can define your own. What if you want to execute something for which you didn't have an alias? Well, we make that easy too. If you simply prepend the exclamation mark to any command, that command gets executed for you at the system shell. And that syntax is valid even in a loop. So for I, range. And hence the beauty of multi-line editing. So as you see, that is very convenient, because I can never remember how to loop in the shell to save my life. I can never remember to do anything complicated in the shell, but I can remember how to do complicated logic in IPython. So by using this, you can basically write the logic in Python and then just execute your system commands with an exclamation mark. And in particular, you can do that. So we support the dollar, we interpret a $sign as, in a shell command, expand the Python variable I to its own string representation, which then lets you do fairly complicated shell scripting without the indignities of the shell. Because now you can write all of your logic in Python, do file name transformations, whatever you want, and then you issue your file renaming commands, and you simply put $signs. Now, if you do want a shell variable, we obviously do let you access shell variables. It would be criminal not to. You put a $, and then we don't escape. We assume that $, means that the shell variable $whatever, but $, are Python variables interpolated into the shell. And this combination can be very useful, in particular when you combine it with this. The fact that you can actually capture shell output simply by assigning with an exclamation. So it's kind of the reverse of the not equals operator, is equal exclamation, and you can capture shell output. And the objects that you get are actually not quite lists. They print like a list, but they're not quite lists. They're a list that has a few special attributes, L, N, S, and P, and they have longer names, that allow you to get the list, the object, is either as a pure list, as a string joined either on new lines or spaces, or as a list of Jason Orendorff's path objects. So these are the kinds of things that are super handy when you're doing shell terminal level work, you're capturing data, and then you want to loop over it in a particular way. So all of these are things, as we said. Yes, question?
Are any of these functions available in non-interactive Python?
Of course not.
So would that main command be awesome in regular Python?
Take it up with Guido. Good luck.
Can you guys expose that in a sort of running and import something and then run against this file which contains that, so type the input with a text file?
So you can, yes and no. Not in things you can import, because we haven't gone as far as modifying the import machinery. But what you can do is if you put a script and you end it with .ipy instead of py, then you can run that script either with the run command or with the shebang and the path to IPython, and IPython will interpret it as an IPython script, will apply its syntactic transformations to it, and then will execute. Because all of these things are valid Python. You just have to call special libraries and do so. If you want to use these things in a script, and there are people who actually write sort of IPython scripts that use all of these tricks and the percent magics and all that, you simply change the extension from py to IPy, and we'll welcome contributions to the Python Emacs mode that supports that. That hasn't been done. Does that answer your question? Question over there.
Yes, so if I had a for loop and I had a lot of calls to the shell with the spang operator, what's the communication with the underlying shell? Is it one shell?
No, it's one shell per call. We're just calling os.system.
So it's os.system for each thing?
Yes, it is.
New shell invocation?
Yes, it is. Now, you can override how the shell is invoked. There is a hook for that in IPython. So it's possible if you have a reason to want a more efficient one that has a persistent connection to a shell, for example, you can pass the right function to IPython, and it will use what you give it for the shell invocations. Okay? Questions? All right. So now I am going to look. I am in 55 minutes, and let me double check everything. So the last two things will be, well, I'll have a quick look at debugging very, very quickly. There's really not much to say other than making you aware of, because the debugger that we expose is PDB, but making you aware of how to invoke it conveniently. So if you run a script that has a that causes a traceback, then even if you've done other work, at any point you can type debug. Debug being %debug, it's a magic. So if you have a variable called debug, you % it. And if you type debug, you end up in IPDB. You end up inside the debugger, okay? And then here you can do the usual things. You can move up the stack, list files, down the stack, quit the debugger. So I actually find myself that most of my work I don't put print statements, and I don't use any other debuggers than this. I run my code, and actually if I want to see what's happening inside a function, I just put an explicit 1/0. And I cause it to blow up, and then I type debug, and then I'm back there, and I can say what is X. Okay, what happened? That was interesting. So I do know that from the Qt console, we do have a few glitches with access to standard in that we haven't been able to completely sort out. In the terminal, it works flawlessly. Every now and then, the whole forwarding of standard input over 0MQ gets a little glitchy, and it hangs as it did in that particular case. And I'm not exactly sure what happened. I don't know why it hung right there. We haven't been able to find what is the condition that makes sometimes that 0MQ socket hang. But the point is, this is how I debug. I move up and down the stack. I look at my variables, and then I quit when I'm done. And I find that to be quicker than either modifying my code too much or invoking external fancy debuggers. I'm sure there are good Python debuggers out there. For the last 10 years, I've gotten by on this, and I find it very fluid and very efficient. So now, let's have a look at how we configure IPython. So you've already seen the terminal console, the Qt console, and this is kind of the bulk of the interactive workflow. Let me remind you, have a look at the question mark by itself, read the little intro, it is useful, and have a look at the quick ref. which gives you a short cheat sheet for interactive work. Now, in addition to that, let me close everything and restart the console again so that you see the message that pops up at the beginning. I guess I could have just started a new kernel. So in addition to that, in the Qt console, you get an extra line that says GUI ref. It's a cheat sheet about the GUI. So if you type GUI ref, then you do get a cheat sheet about the graphical console, which, as you see, is actually better formatted. And that's because this is a Qt rich text widget that can format HTML. So that quick reference is restructured text, and we format it with docutils to show it to you nicely. So here you have a short mini manual for the Qt console. These references are meant to be very short so that they only take 5 or 10 minutes of your time, and I promise you'll learn a few useful things. Oh, a couple of important things before I move on to configuration. These numbers right here are there for a reason, and it's important to know about them. You know that in Python, the last result that you execute is always the underscore, right? Well, in IPython, we also have the 2 underscore, which is the next previous result, and the 3 underscore, which is the next previous result. But obviously, 20 underscores would be silly, so we only have 1, 2, and 3. But what we do give you is underscore and any number. So if I want this result, I can just type underscore 4, and that's not special syntax. These are actual honest-to-God variables. We dynamically create these variables for you in your namespace. The point is, often when doing scientific work, you compute something which may take a while, and this may be true in other contexts, but you forgot to assign it to a variable, and you want to reuse it afterwards. Well, you don't have to recompute it. IPython has it cached in these underscore variables, and it does that for all of your outputs, their underscore and the number, and all of your inputs as well. So underscore I is, for example, I5 is the string that was the input to line 5. So if I say print hello, underscore I9 will be the string print hello, which means you can exec them. And the lists in and out, the objects in and out actually exist. So in exists, and out also exists. The reason why we created the underscores is because, and the underscore i's is because A, they're much quicker to type than out bracket 4, and second, because variables called in and out are easy to clobber. It's very possible that one of your codes will have a variable called in and out, so we decided to also have these other names that were much less likely to be clobbered by your own code so that you could refer to them. I find these features extraordinarily useful, and I use them all the time. So, and because these are actual Python code is stored in there, you can actually use exec. So for example, you can say exec in 9, and it will execute that line, right? Because it's just a string. Yes, question?
What if the expression was an IPython expression, like your echo inside the for loop that you had?
So let me just print it. So what it does is it stores the transformed version of it, which is now valid Python syntax, so that it can get immediately executed. So that's not what I typed. That is what gets stored in this variable. Okay, so now I'm going to spend the last few minutes showing you how to configure IPython. So I'm going to exit here. And so where is your IPython configuration information stored? It's stored in your IPython directory. And your IPython directory, it is operating system dependent. So probably hey man, what's the quickest way to find the current directory? Within IPython, right? It's just to print IPython dir in IPython itself, or to create a profile and see what gets printed out. What do you think? No. This is probably the easiest way to get it, right? So in the namespace, there's always a getIPython function that you can call, and that gives you a handle on the IPython object itself. And it has an attribute, which is, where is your IPython config directory? Because that is platform dependent. There's no generic, the policy for resolving that path is documented in our docs, but the easiest way to get it is simply to to ask for it. So let's have a look at that directory. And we'll see what's in there. So in your directory, in your IPython directory, you won't see some of this gunk because these are the old configuration files that we don't use anymore. I keep them around because I occasionally have to test old versions if somebody reports a bug. So I do keep them around. But you should see mostly only directories called profiles. And so the way IPython works is it uses a concept of profiles. We don't only support one configuration. You can have as many configurations as you want. The reason for that is because it's very common for people to want to define a bunch of things that get loaded at the same time when they start IPython. But for different projects, they may have different requirements. So we allow you to define a profile that is all of the combination of things that you want for a given project, config settings, files to load, and all of those go into that directory. The history gets saved in that profile. So if I go, when you start by default, you get the default profile. But you can create arbitrary profiles, and in the profiles you have the SQLite database of your history for that profile. All the sessions from that profile are stored there. The config files for the basic IPython, for the node, the Qt console, and for the notebook, as well as some other directories, including, for example, the startup directory, where you can, any Python file that you put in startup will get executed when IPython starts. So this is the simplest way to drop execution code. And variables that you put in there, if you define a variable there, if you import a package there, you drop a script in there, it just gets executed at startup time, and everything in that namespace in that script becomes visible to you. It's as if you had typed run that script on the first line of IPython, but we load it for you automatically. So let's have a look a little bit at how we configure IPython. Before we dive into the config file, obviously you would expect IPython to be civilized enough to show you some help. If you call it with --help, we don't pipe it to a pager because we don't quite assume that you're on a Unix box, so you may want to pipe that to a pager. So when you start IPython, the help with --help, the help page is fairly informative, and IPython has a notion of subcommands. The Qt console is a subcommand. There's actually a console command, which is a text terminal that also runs with a separate out-of-process kernel. There's the notebook. You can start a kernel by itself, and there's a profile command to create and manage your own profiles. And then it has many command line flags, like any kind of reasonably complex program. It has its own list of command line flags. They're all listed here. And for example, the --pylab flag that I used earlier, it has quite a few. But then you will begin to see some other flags that look a little bit different. And so for some of these other options, what you see is the short name here, and in parentheses, you see a name that looks a little bit longer, that looks like Python code, and actually default values that can be, for example, in this case, whether to automatically call functions without forcing you to type parentheses. It says it's an enum, the actual class is this one, and these are the possible choices. The way this is being generated is because IPython actually is introspecting the objects that define this, and we use a system which is basically a lightweight implementation of Enthought's traits machinery to define all the possible values for all of the classes, and we pull this documentation out of the code internally. So there's no duplication of information. The classes that define the behavior are the thing that gets introspected to show you the options. And so some of the flags simply are simply passed like this in classic Unix mode. But for more complex things, this is the form which you can call, and with this call form, you can control any aspect of IPython. So when you type --help, you only get this form. And so you can say, for example, IPython --autocall 0, and that will set autocall to 0 so that IPython doesn't automatically call functions by default. But you can equally say with the long form for autocall, which is interactive shell.autocall. And here, you basically have to type a valid Python string, because this little snippet of code will get executed with exec at that point in the code. Let me put this at the top so those in the back can see better. In here, you do type a valid Python string. So the point is, and it has the exact same effect. So what is the idea? For the things that have these short, sort of classic Unix style flag behavior, you can use that. But we couldn't really make short forms of every single object class and attribute that we have in the code base. So for everything, we've made these short aliases for the most common features, but for the rest, you do have to use this, you do have to use this long form right here. And you can actually ask IPython to show you what the long form is for everything available. So if instead of help, you say help-all, help all, then IPython will not just show you the basic ones, but it will actually dig into, it will introspect itself, and it'll find for each of the classes that make up the application that you just called, it'll show you everything available, okay? Absolutely everything that is configurable is printed for you there. So anything that is configurable within the code base can be overridden at the command line with the long class form name. And the reason why understanding that is important is because that is exactly what the configuration files use. So if you want to permanently set a flag, not always set it at the command line, but permanently change it, you want to edit that value in the config file. So let's all make a new profile, because you may have already one, so let's make a profile. How do we make a profile? If you say IPython profile create PyCon, then it'll take a minute, and IPython will say, I've made a profile, and these are your config files. So now, I have a PyCon profile that was just created, and IPython makes the config files for you in that directory. So now you can edit those config files. And so I am going to, did everyone get that? Because I'm going to switch to my editor, so I want to make sure that everybody got the profile create command. So now I'm going to open those with my editor. Because I'm just about running to the end of my presentation. So here, this is what one of these config files looks like. These are valid Python files that we execute in an almost empty namespace that has a few handy things. In particular, it has a getConfig call that sets a variable called C, which is the configuration object. And this is the object on which you set all of those attributes that you could set at the command line. You can set them here. All you have to do is uncomment them. So if you say, let's find, for example, if I want to change the color scheme to be not from Linux, but to be light background, I can set that here. And it tells you, as you can see, it tells you what a little doc string and what the valid choices are. All of that is auto-generated from the class itself. So none of this information is redundant. Titus?
So this is going to be an annoyingly broad question. How often, this is really cool, how often do you end up using it and what for?
I do have profiles set. So I do configure several of my defaults are different from the main defaults. And for projects, I will often make a profile so that it preloads a bunch of things specific to that. And for example, may activate logging, because the way you start with a profile is now, for example, I have changed, if I start IPython, by default, my colors are for a dark Linux terminal. I can overwrite that by saying --colors lightbg, and then I get light background colors that read better on a light background terminal. But I just changed here permanently in my config file for the PyCon profile that. So if I simply say --profile PyCon, then that is what gets loaded. Ignore these warnings. It's telling me that I have config files in the old format. But I don't want to get rid of them because I use them for testing, for debugging old stuff. And you can actually turn the warnings off. The point is, it told me you've loaded the PyCon profile, and I have that option set. So if you have two research projects where you would like your sessions to start right away with a bunch of data files pre-configured, you may want to have a database connection open right off the bat. You may want to activate, I don't know, turn on your EC2 stuff in the background. You can say just IPython profile so-and-so, and that's it. And you get everything configured for you in one shot. Brian is going to show you how to run the notebook in secure mode. So where you run the notebook on a public IP address with SSL turned on and with a password. I have a profile called NB server, where I say IPython-notebook NB profile NB server, and instead of my local notebook, I get the remote one that I can give the URL to a colleague, right? So it is very handy because it's a way of organizing history. Everything goes into those directories and they don't clobber each other. Okay? So in general, I'm basically run to the end of my time, but the point is, this is valid Python code. These files are auto-generated from the real code. They're completely documented. And because they are real Python code, you could decide, I want my colors to be light background if I'm on Linux, but if I'm not on Linux, but Linux otherwise. So you can say import OS if os.name equals blah, blah, blah. And I'm not going to try to do it here, right? Et cetera, et cetera. You can put any Python code you want here. These are valid Python code files. They get executed as normal Python files. They just have a couple of things defined in their namespace, such as getConfig, and a command to load another config, so you can basically have a profile based off of one another. So you could have your default profile define the basic stuff you like, and have others that only override a few things without having to copy all of it. There's a load subconfig command, but you can read that in our docs. So we've run about 1 hour and 10 minutes since the start. We're going to take a 5-minute break now, and then the next session, Brian will take over with the web notebook. So now we've covered the terminal, the configuration system, and the Qt console, and all of the main of interactive use. We're going to give people a chance to go to the restroom, and we'll see you in 5 minutes. Anybody who wants to come up and ask me a question, you're welcome to. In the meantime, Brian will set up.
Tell you about the IPython notebook. And we want to do a spot installation check again. So if you came late or you're having trouble running the IPython notebook, I'll show you how to get that started. How's the font size on my terminal in back here? Bigger? Better? Even go bigger. I'm not going to use the terminal too much, So if you type IPython space notebook at the command line, you should see the following. Now you may have to, depending on what system you're on, I've got a bunch of error messages here. Well, I'll show you how to find it. So you may have a startup that looks like this, and it will actually display the URL that you need to go to if your browser doesn't open up automatically. So if you're having trouble getting this going, please raise your hand, and we'll have people come around and give you assistance. We really want you to be able to follow along with this part of the tutorial. And also, Min's part of the tutorial on the parallel computing capabilities of IPython will also use the notebook. And so now's a good time to make sure that that is working. All right, so the IPython notebook.
Brian, do you want to explain that the mathjax message is kind of harmless because some of them are getting it? So.
Yes, I should actually mention that. So a soft dependency of the IPython notebook is the mathjax library. Mathjax is a JavaScript library that renders LaTeX in the browser. We don't include that with IPython because it's a relatively large download. I think it's close to 200 megabytes. Don't all of you go and try to download mathjax right now. If you start the notebook without mathjax, you'll get a warning. You can just dismiss that warning without any consequence. You just won't get rendered LaTeX math in the notebook. And I'll talk a little bit more about how to install mathjax here in a second. So the IPython notebook is something that Fernando and I have been thinking about for a very long time. And both Fernando and I came out of physics using Mathematica and really loved the workflow of the Mathematica notebook. We discovered Python in the early 2000s. Fernando started IPython. Both of us really fell in love with Python, but missed the workflow that the Mathematica notebook had. And so adding that capability to IPython was something that we had thought about for a long time. And if you're not familiar with Mathematica, I think you'll see fairly quickly what the notebook user interface looks like. It's basically, for us, it's a web-based user interface for IPython. It has all the same IPython goodness that you've seen from Fernando. but it has sort of a different workflow that's more document-oriented. And so the notebook web application is really a document editor, and the notebook files allow you to combine code with rich text, inline mathematics, inline plots, HTML, Markdown, and basically any MIME type that your browser supports. Store all that information in a single file, save it in version control, redistribute it to collaborators. This is built on top of the same IPython kernel that the Qt console is based on. It is a web server that we've written based on Tornado, WebSocket, ZeroMQ, and it's currently really a single user application, but we are working on more and more multi-user features for the notebook. A bit on the installation. So the notebook requires Tornado version 2.1 or higher. It does require ZeroMQ and PyZMQ, as does the Qt console. So the only additional requirement that the notebook requires over the Qt console is Tornado. And it also requires a recent version of Chrome, Firefox, or Safari for the WebSocket support and also the flexible box model. I guess there's an issue with a particular combination of Safari, IPython, and Tornado. If you have the latest Tornado, IPython 0.12, and Safari, the notebook won't work because of an issue with the particulars of some of the WebSocket versioning. But the latest IPython development version, latest Tornado, and Safari seems to work fine. So. The notebook also works out of the box with both EPD and EPD free. MathJax is another optional dependency, as I mentioned before. There are two ways that you can run MathJax. One is through their own CDN. That will pull it over the internet every time you run the notebook. Most of the time, though, we recommend actually installing MathJax locally. You can do that by firing up IPython and executing these commands. Don't do that right now. That will download the full 200 megabyte MathJax, and if you all do that, we'll bring the network down. So I want to spend some time talking about basic notebook usage. And the first concept in the notebook is that a project is a directory. And so if we go back over here to the terminal, and I'll do this again, and I do ls, print working directory. Here is a directory on my file system that contains a bunch of notebook files. Notebook files have this .ipynb file extension, and if I want to access the notebooks in a particular directory, I can start the notebook server by typing IPython notebook. And immediately we're taken to the project dashboard, as we call it, that displays all of those notebooks. Now you may be wondering, well, what if I have multiple directories? Do I have to really shut down the server and change directories to access the other notebooks? The answer right now is yes, this is something we're working on. We're going to make it so that you can actually browse your file system as well. That's a huge feature request that we have. And then to create a new notebook, you can just click New Notebook, and you'll get a new blank notebook here. And the basic idea is that this should look and feel just like the regular IPython. All the usual commands that you're used to with IPython will still work, except for one difference. If you press return, code will not execute. We follow the Mathematica convention that shift enter does the code execution. So there's one minor difference over the terminal in terms of executing code. Obviously, the reason we do this is to make it nice and easy to edit multi-line code inside the notebook. Each of these areas here we call a cell, and that's sort of the fundamental unit of the notebook. That a notebook is basically a linear sequence of cells. In the version of the notebook you're using right now, 0.12, there's two cell types. There's a code cell type, which you can select with this button here, and then there's Markdown. And I'll talk more about Markdown in a second. I'm actually going to go over here and go to this notebooks here and show you a few things. So Again, the notebook works just like regular Python, regular IPython, so we can define a variable a, we can print a, and then another way of seeing the value of a is just to return a from the Python prompt here. And notice the difference here. When I print a, I'm getting something that's being written to standard out. That's displayed differently from when I return it as the last variable in a cell. When you return it and see this out prompt, it's actually triggering a very complex part of IPython that we call the display system or the display protocol. And in standard IPython, or standard Python and the terminal-based IPython, whenever you see an out prompt, something inside Python called the display hook has been triggered. Basically what the display hook is, it's the function that gets past the object that's returned. The default implementation version of the display hook is to return the string representation or the repr of that object. As we'll see shortly, the notebook has a much richer display system that actually allows many different MIME types to be returned from the display hook. Again, you can do things like print PWD, you can list your files. Basically everything in IPython should just work. Just to show you that the standard out is being brought back to the notebook asynchronously. Here's a simple example of that. And there's a lot going on behind the scenes here. We're using 0MQ socket to talk between the kernel and the notebook server, and then we're bridging those messages over WebSockets to bring it back to the browser. And that gives a very interactive, very live experience, and hopefully for the most part it shouldn't behave any differently from the regular terminal-based IPython. One thing Fernando mentioned before, we currently don't have raw input working in the notebook. We know how to do that. We just haven't gotten around to implementing that. And so that is a limitation. And actually, one important point about that limitation is that if you type %debug in the notebook, it uses raw input, and so you're not able to do debugging in the notebook. And I'll show you a workaround here shortly. So, again, you get the nice tracebacks. So the area here is called the left panel, and you can see there are different sections. The left panel can be collapsed by clicking on this divider. Don't get too attached to the left panel. In the development version of the IPython notebook, we've gotten rid of the left panel and moved to more of a menu-driven and toolbar-driven approach. It's a much cleaner UI. I think you'll like it. We were tempted to use this with you, but it is development code, and we wanted to stick with the latest stable for this tutorial. So you can create new notebooks. Open an existing notebook takes you back to the dashboard. I'll talk in a little bit about the notebook formats and downloading. The print support opens up a separate window that has a slightly simplified user interface that's useful for printing. Honestly, the print support right now is a little bit lacking, mainly because of pagination issues. If you have longer cells or plots, different browsers are not that great at paginating things like that, so you often get plots that are cut in half or cells that are cut in half. That is something that we're working on. As far as we're concerned, the main path forward for getting high-quality PDF output out of these notebook files is to go through something like Sphinx to PDF and actually have the pagination handled through that route. There's different cell level actions. So let's see here. We can, let's say we want to insert a cell below here and print high, and then we decide later that we don't want that cell. We could delete that cell, and that's deleted. Maybe we want to move some cells around, and so there's a move up. It will actually move the cell up in the notebook. There's move down. If you don't remember the Shift-Enter keyboard shortcut, there's run selected. For the code cells, we use the fantastic Code Mirror JavaScript code editor. That's how we're doing the syntax highlighting here. It also supports auto indentation. There are some newly released Emacs and VI bindings for CodeMirror. We haven't taken the time to actually implement those. But if you're interested in that, that should be something that comes in the future with the notebook. What else? Oh, I should mention the toggling of output. If you click on a cell that has an out cell, or actually any output, and you click toggle, that output will be hidden. It's still there, it's not deleted. That's useful when you have a cell that has a lot of output and you want to hide it. Clear all actually goes through and removes all the outputs of all the cells. I'm not going to do that right now. So I think that's it. I'll talk about Markdown in a second. So the kernel. The kernel is an important abstraction. So let's say we're running a command, and notice that you can see up in the corner here, we see that it's busy. We want to interrupt that. We click interrupt, and this actually sends a SIGINT to the kernel and interrupts it, and so you see a keyboard error. There's other times, though, where a keyboard interrupt is not quite enough, where you actually want to completely bring down the kernel and start from scratch and bring it up again, and you can do that simply by clicking restart. And the kernel, when you click restart like that, it actually shuts the kernel down, fires it up again. This is really useful when you're editing a lot of code in a separate editor, and Python's, I think Fernando mentioned it a little bit, the limitations of reloading edited modules in Python. And so if you simply restart the kernel, you don't have to worry about that. Everything starts from scratch. You have to rerun your cells again, but this is a usage pattern that we actually use fairly often. Yeah?
I'm sorry, is there an easy way to rerun all your cells?
That would be run all. So, yeah.
If you restart the kernel and run all,
Yep.
will it renumber the cells?
Yes. So the numbering of the cells is related to the particular instance of that kernel. Yeah. Yeah.
And when you load a notebook, variables and what's been done isn't necessarily in your active environment.
It depends. So the default behavior of the notebook server is that when you close a notebook, it leaves the kernel for that notebook running. So if I were to close this notebook right now, reopen it, all those variables are still live. If you shut down the notebook server itself, everything shuts down. And you'll have to re-execute the cells to get the variables in the namespace of the kernel. Yeah? Yes, it runs sequentially from the top to the bottom. It doesn't try to look at the input prompts to see the order you ran them in previously. That would actually be quite difficult. All right. So we do have some help links here. These 6 links take you to the typically the Sphinx documentation for these different projects, which sort of the core projects in scientific computing. I should note, there's sometimes when you're working in the notebook where you want more of a terminal feel. In other words, when you execute a cell, you don't want the next cell to be selected. To get that, if you simply, instead of doing Shift-Enter, you do Control-Enter, the same cell stays selected, and actually we automatically select the text, so if you want to immediately type something different, you can just start typing and it will overwrite the previous command. So that's Control-Enter. We also have keyboard shortcuts that actually really simplify working with the notebook. The general idea with our keyboard shortcuts is that it's rather difficult to find keyboard shortcuts that don't conflict with the operating system's keyboard shortcuts and the browser's keyboard shortcuts. And when you're designing a web application, you have to worry about the keyboard shortcuts not just on one browser, but all browsers. There's not many keyboard shortcuts that are left. So the route that we chose to go with is to have one top-level keyboard shortcut, namely Control-M, and then another key after Control-M that actually does the particular action. So Control-M, A and B, insert a cell above below. T is toggle. You can toggle line numbers. I think that should work. If you Control L. You can actually see line numbers here provided by CodeMirror. Code cell is C, markdown cell is M, select previous next, there's interrupt kernel, restart kernel, and so I think you'll find that once you start working with the notebook a lot, you'll do a lot of these things using the keyboard shortcuts. At least that's how we've ended up working. So, show you how paging works. Yeah. What's that? No, it's not configurable right now. So you'll remember in terminal-based IPython, when you do question mark, you get a pager that opens up with the help of that. Our pager is a sub-window down here that pops up, and you can collapse that. It's actually hidden the whole time, and you can bring it up and down with that. And, well, so I guess this is worth mentioning. So when the kernel is running, we actually run a separate thread that does not hold Python's GIL that responds to a heartbeat message. Repeat the question. Okay. Okay. Thanks. So we actually heartbeat the kernel process so we can detect if it seg faults, and the notebook automatically handles restarting of that. So here's a simple example that will actually seg fault the kernel, and after one heartbeat interval, the notebook server should notice that the kernel's not running. We detect that and actually give you the option to restart the kernel. You may wonder, why would you want to continue to run without the kernel? It probably shouldn't be there, but you can save the notebook even though the kernel is not running. So you may feel like, well, I don't want to restart it, but I do want to save it. In this case, we will restart. So markdown cells can contain basically arbitrary markdown syntax and HTML. Markdown is a very lightweight markup language. You may be wondering why we did not choose restructured text. It turns out that in this context, restructured text is basically broken. And the reason that is that in restructured text, heading levels are not absolute. You can basically use whatever markers you want to indicate a heading level, and that basically makes it impossible for us to render restructured text cell by cell. If you entered a heading 1 level in one cell, and then in the following cell you did heading 1, heading 2, heading 3, there's no way for us to detect that heading 1 in that first cell is somehow related to the heading in the other cell. In the development version of the notebook, we do have a way of handling restructured text, but it's not rendered in real time in the notebook. You would actually have to use an export mechanism to restructured text and handle it separately. So let's look at a markdown cell. This is a formatted markdown cell or a rendered markdown cell. If you click on that, you actually see the source, and this here is a bug in 0.12 that's fixed in the development version. There we go. And so you can see Markdown is a very simple markup language. To get heading levels, you put the pound symbol between 1 and n of those, depending on the heading level you want. There's italics, boldface. You can build lists. You can indent code blocks. And when those are rendered, we actually have a syntax highlighter for those as well. So it's really nice. You can actually mix live code in the code cells with sort of code that's more static and can't be executed in the markdown cells. As I mentioned before, with MathJax, we actually have math support. So let's actually do that. There we go. And so you can actually put single $signs surrounding LaTeX math, or we also support double $signs for the other equation mode. And when you do Shift-Enter, which is like execute, in this case, it basically means render, those things get rendered to LaTeX. And so you can really start to see that the notebook gives you a very rich environment for dealing with code, math, and inline text It's a very literate programming environment that works really well for exploratory, sort of interactive scientific computing, which is a lot of the usage cases that IPython is really targeted for. All right, so let's see. I should mention, here's save. You should be a little bit cautious right now about saving your notebooks, a little bit paranoid, I would say, for two reasons. One is we do not have an autosave mechanism implemented right now. So if you open a notebook, spend 5 hours working on it, and don't save it, it will go away. The second is that when you go back to the terminal and you realize, oh darn, the notebook server here is running, I want to run something in the command line, and you do Control-C, all of your notebooks, all of your kernels just got clobbered. So this is something that we're aware of and that we have been bitten by, and it's something that we're trying to figure out. Yeah, I mean, how do you shut down a command line program but actually try to guess when the user didn't really want to shut it down? So we're exploring different ideas about handling that, but you have been warned.
Is Control-C the normal way to shut down the kernel?
You mean the entire notebook server?
Yes.
Yes, that is the current way that you shut that down. All right, so let's go back here and see where we're at. Keyboard shortcuts. So I think I showed you the no browser option. That is if you want to open up the notebook and not have it start up the browser automatically. There's another command. Well, we'll get to that in a second, actually. All right, so notebook files. I want to talk about this a little bit. We have worked really hard to come up with a notebook format that makes sense. This is very difficult. Our notebook files can contain PNG, JPEG, SVG images, HTML, Python code, LaTeX, and so we need a single file format that contains all those things. Naturally, you'd start to think, well, there's going to be some binary file format that has some complex structure, or maybe you put everything in a directory and you zip it all. And there's one problem with that. You can't version control that. And being scientists, we want to version control everything. And so the option that we've gone with is actually a JSON-based file format, and we base 64 encode all the binary blobs, and it's a wonderfully simple way of storing this information. Let's just, I'll show you what these files look like here. There we go. So here's an example of one of these JSON files, and you can see here, this is a code cell or cell type code. It's not collapsed. Here's the input, the outputs. There's many different types of outputs. We support the different MIME types. I'll talk more about that in a bit. And if you go down here, I think there's an image. We've also made decisions such as if you have a multi-line input, each line of that input is stored on a separate line in the notebook file, so that when you change a line in a particular code cell, just that line is diffed in your version control system. So that's what these notebook files look like. And let's see here. I guess I want to go back, start up the notebook again, and type script here, and I'll show you a few things. So let's say I want to look at the SymPy notebook here. And over here, you can download the JSON file here in the IPython option, and there's also a Py option, and let's download that notebook. And show in Finder, we don't need that version of it. Let's drag that over here to TextMate. This allows you to export your notebooks as plain Python files. Now you may be thinking, how on earth do you do that with all the rich data types, with images? So one, the Py file format simply removes all the output. So all the output you have, the images, the standard out, those will be missing from your Py file. We do, however, include markdown cells. And so you can see here, it's sort of a lightweight markup that we have for these file notebook formats. You can indicate a markdown cell using this syntax, a code cell indicating that. And in this case, our markdown cell actually just had valid HTML. And I forgot to mention that. Markdown is a superset of HTML. So when you're typing in a markdown cell, you can put any HTML as well. And that makes it very flexible to deal with these things. So for example, you might be giving a talk during another really, where'd that go? There we go. So you might be giving a talk during another talk and actually want to embed an iframe of the other talk and actually see sort of what's going on to see if there's anything interesting. And if you scroll down to the bottom here, there you go. You can see there's a little bit of HTML in the markdown cell. So you can put anything you want in these markdown cells, including other embedded web pages. It actually gets better. Yeah.
I just heard Dave Beasley going, what is going on? So that's a bad sign.
Okay. Yeah. There's a lot that's possible with the notebook. And remember, this is running on your own system right now. Yeah. All right, so, we were looking at the PI file format. If you start the notebook with the script option, every time you save a notebook, it will automatically save the .py file version of that notebook alongside of it. And so that's really useful if you're collaborating with people who are not using the notebook, but you still want the flexibility of being able to use the notebook. You can actually export these files. To import these files, let's attempt to go through that process. It's so we've got that. And actually, I'm going to rename this, call it SymPy2. And if I simply drag and drop that to the list here, we can upload that. And now when I open that, it's been imported to a notebook file. And it works just like you would expect. Eventually, we'd like the ability to not have to do that extra import step so that you'd be able to, from the project dashboard, actually just say, I want to open that .py file as a notebook file and have the import be automatic, but also when you save it, maintain the fact that it's still a .py file. So lots of code yet to be written. Let's see here. So these notebook files are very simple to read and manipulate. Here is the Python code that you can use to do that. And actually, I will, this. So here, I import the NB format module. I should mention these notebook files, the file format itself is versioned. This allows us to continue to modify and expand the capabilities of the notebook format and have some chance that we can handle conversions between the different versions of that. So here we read it. Here we can see the top level keys. And here I can actually pull, there are the top level abstraction in the notebook is a worksheet. We don't have worksheets implemented in the user interface yet, but worksheets have cells. And it's basically in Python now, it's a dictionary object that has the information about that cell. Part of what we wanted to accomplish with this file format is that we want to make it easy for people to write importers and exporters. And this is something that we would love help with. We've got a rough sketch of an exporter to restructured text, to LaTeX. We really want to have static HTML export to make it easy to render notebooks and include them as static HTML in other web pages. And there's a lot of other formats that people are interested in. And that's something that we're actively working on. And in particular with this, we'd love help. So I guess the only other thing I haven't mentioned with importing and exporting is the notebook magic. The good news is if you open up the terminal-based IPython, start to type commands, and then you type %notebook-e for export and the name of a notebook, it will take the current history of your IPython session and export it as a notebook. The problem is it actually is broken both in 0.12 and the development version. So if you go try this, you'll be disappointed. But this is a feature that we do plan on supporting. It's interesting what you discover. It used to work, really, I promise. And it was really cool. Yeah, so one thing we're finding is that IPython as a project as a whole is really difficult to test. We've got very complex networking code going on, things in the browser, things in Qt, user interface, and it's a hard problem. It really is. I mean, a lot of the core of IPython does have tests. A lot of the network-based things and more GUI and browser-based things are not tested very well, and so we run into situations like this. So there's some notebook-specific magics, and actually not all of these are notebook-specific, and I want to show you these. So let's go back here, and let's just start a new notebook. The first thing that you want to know about is if you want to do interactive plotting in the notebook, you need to run the PyLab magic, and you can specify a matplotlib backend. The backend that you probably want to use most of the time in the notebook is the inline backend. So if we run this, we can make inline plots. This basically imports things from matplotlib, NumPy, and is the same experience that you get in the terminal-based IPython, except for the fact that the plots are inlined. We can throw that away, and I want to show you one other thing about PyLab. So PyLab Qt. Here we're going to use the Qt backend. The kernel is running in a separate process. It is completely decoupled from the HTML notebook's user interface. So we can start the Qt backend, and you probably noticed that this opened here, and I can make a plot, and now this opens up in Qt, and you can actually interact with it interactively. So if you need the interactivity of plotting libraries like Matplotlib, you can still get that by selecting the proper backend. All right, so I did want to mention briefly the integration that we have with SymPy. SymPy is a symbolic mathematics library, and SymPy objects know how to render themselves as LaTeX. And this starts to get into something that we call the display system. And so here we can enable this special mode, this special display mode for SymPy by typing %loadExt. This is loading an IPython extension, SymPy printing. We're going to create some symbolic variables here. And when we go down here and start to enter interactive SymPy commands, the output of that is automatically rendered to LaTeX and handled by MathJax. So this makes it, I'm a physicist, I do symbolic computing as part of my research. The notebook makes it just absolutely fantastic to do this type of work. It seems to work really well. You can see And actually, I should say, the reason this works so well is that MathJax is spectacular. It really has transformed web-based mathematics. There are some things that MathJax has, a little bit of difficulty handling, but for the most part, it just nails it. Showing you other examples here. Here was a longer example using SymPy to do some Taylor series expansion, inline matplotlib graphics with that as well. So, let's see where we're at. Oh, yes, Qt console. One question is how to deal with the fact that there is no raw input. And if we go over here, open up a notebook, and let's say we're working in the notebook, and we would like to start to do %debug and interact with the code using the Qt console. If we type %Qt console, you obviously have to have PyQt, SIP, and Qt installed for this to work. You do that, and you actually get a Qt console hooked up to the same kernel, and so immediately you can do %debug and actually debug your code and have access to other libraries that use raw input. All right. So, oh yeah, load Py. Yes.
I've been just playing around a little bit as we're going along, and I think I already have 30,000 tabs open.
That's a lot.
Is this a known issue?
Well, this is something that I think will remain. There's some question about this, and one of the design goals that we had with the notebook is that we wanted a simple, clean user interface. And actually, the user interface that you're seeing right now is rather ugly. I'll show you the new user interface that's in the development version of IPython. I think you'll see that it's just simple and clean. And the history of IPython is that when you type IPython at the command line, it's simple, it's clean. It sort of gets out of your way. It's not like starting up Microsoft Word where you get lots of widgets and things here jumping out at you. And we really want that. The difficulty is that it's difficult to pull that off and to put a full file browser in the same window as the notebook. And so right now we've chosen to put the project dashboard and the browsing of notebooks in a separate page. And that means it's a Google Docs-like experience. So when you open a new notebook, you get a separate tab. In principle, we could allow the new notebooks to open up in the same tabs. I don't know. We're still trying to get a feel for that. But we do, we're acutely aware of this issue, and I don't know. We'd love ideas on how to handle this. Yeah.
Just going back to the PyLab.
Yeah.
If you're more accustomed to using the OO PyPlot approach, how do you get that to work and to create plots?
So the question is, if you're using the object-oriented API for Matplotlib, how would you do that? And I think the answer is that, and maybe Fernando can correct me, is that PyLab should set up all of that just fine. You'll just have to say from Matplotlib, import the classes you want to use, and then use them. One thing that is important to know is that when you're using the inline Matplotlib backend in the notebook, we automatically call show for you. So that, I don't know, is that a good summary of?
Real quick, I know this API probably better than you. So, if you want to use the more object-oriented API, the typical way to do it is probably to call subplots and grab a figure and the axis, and then use this, which then gives you standard display. But now you do have the axis object, but importantly, you also have a handle on the figure. And Brian is going to get into the display protocol in a second. But so I'm stealing a little bit his thunder here, but it's because the figure object itself knows how the representation of the figure object is the drawing of the plot. So if you use something that gives you the figure and the axes, and you can have one or more axis objects, then you can write in your cells, and in the notebook, this is actually how I'm working these days. I'm always using subplots. I get the axis. I do within one cell, and the cell can be long and complicated. I do all the drawing. At the end, I get the rendering, and I have a handle on the figure object in case I need it later. So this is how I'm working with the OO API.
And to get this to render properly, you just have to call Pylab inline initially.
Yes,
Yes.
that's correct.
Yeah.
Or start it with, if you want it permanently, you can start it with -- pylab inline at the command line, or you can turn it on with pylab inline.
So you only need,
that's right.
you only need Pylab inline for the first plot. The second plot will always work no matter what backend you're using.
Sure, yes.
Yeah,
So the representation of any figure, no matter what backend you're using, will work like this.
yeah. And again, I'll talk about the display system because there's a lot going on underneath the hood with that. All right. So, yeah, I'm wondering about time. How do you, it's
I think you have about 10 minutes.
10 minutes?
And LoadPy with something like the Matplotlib gallery or the scikit-learn gallery is so incredibly useful.
Yeah, I think I had, well, I'll just go down here. So if you have a Python script somewhere in the universe, it can be in your local file system. You can also pass LoadPy URLs. You can simply type LoadPy my script, and it actually imports that Python script as a new notebook cell. So I have a matplotlib example here. And we can go back and paste that. And we actually get the matplotlib example, and we can type shift return and run that. So it makes it really nice and easy to import other Python code into a notebook session. And LoadPy works with Qt console as well, right?
LoadPy works in the terminal.
And it works in the terminal console. So, yeah, so nice magic function. All right, so there's two main things I would like to cover, and I think I'll spend about 5 minutes on each of them. So the first is how to run a secure public notebook. By default, the notebook does not use encryption, does not use a password, and it only listens on localhost. So when you type IPython space notebook at the command line, you are secure, but you're not going to be able to share that with anyone outside your local system. There's two ways of securing the notebook, and we highly recommend using both of them if you're going to run this on a publicly facing system. The first is password protection. The second is SSL encryption. And there is 5 basic steps for running a secure notebook, and I'll run through each of these steps. The first is to create, or we recommend creating a custom IPython profile to maintain the configuration. The second, you're going to create a password. Third, you're going to create an SSL certificate. Next, you need to configure the profile to tell the profile about this password and the certificate, and also configure the IP and port, and then you can start the secure notebook. So, to create a profile, you're simply going to type IPython profile create NB server. The profile system, as Fernando mentioned, is the general way of maintaining sets of IPython configurations. It's also the same system that's used to configure the parallel computing support that Min's going to be talking about shortly. So here we'll say I created an NB server profile. To create a password, you'll need to use a utility that IPython has for giving you back the hash of the password. That is what you'll need to paste into the configuration file. This information, all of this information here is available in our online documentation. And so, I'm going to go a little bit fast through this, but you can access that information there. So we'll create the password. You'll need an SSL certificate. So either you can figure out how to get one that's signed by the appropriate parties, or you can create a self-signed certificate. On Mac and Linux, this is fairly straightforward using the following command. And on Windows, we have no idea how you would go about doing that. Maybe someone here could, yeah. Fantastic. That's a very simple answer. Yeah. All right, so we have a certificate. So how do you configure the profile? So this is a standard configuration IPython config file. And actually, let me just go and open up this. Let's go cd profile nb server. And open up TixMate. So when you create a new profile, we populate that profile directory with an IPython notebook config. This file has all font.
Being recorded, so.
Yeah, let's, we can close that. There we go. This config file contains all the configuration options for the notebook. They are documented here. I'm not going to spend a lot of time, just highlight the main ones required to run the notebook in secure mode. Here, we've specified the hash of the password. Here we give the full path to the certificate, and notice in this case I've actually put the certificate in the profile directory. Might as well put it there. You'll remember by default the notebook server listens only on localhost, so you need to change that to either put star to listen on all interfaces or to put the IP address of your public-facing network interface. Here I'm going to set open browser to false. No reason to start the browser if we're going to basically run this publicly and allow people to access it through that. And I think that's about it. Well, I guess you can also set the port, notebook app.port. We recommend setting it on some fixed port that makes sense. You will need to have your firewall open to that port as well. There are other options in the config file that are useful in running the notebook publicly. There's some configuration that you can make with the URLs that are used, the base URLs. There has been some attempts to run the IPython notebook behind Apache. It was not successful. The main issue, I think, is going to be figuring out how to proxy the WebSockets through. We just haven't looked into that. We're hoping that eventually someone will tackle that problem and that it will be solved. Once you have done all the configuration, you can start the secure notebook by simply doing -- profile and pass it the name of the profile. So I don't have much time to talk about the display system, but basically IPython overrides the display hook, and our custom display hook looks for special methods on objects that allow those methods to declare different representations other than simply the textual representation. The current representations that we support is plain text, HTML, SVG, PNG, JavaScript, JPEG. So someone said it's a bit crazy that you can have arbitrary HTML. You can actually, in the development version of IPython, have Python objects that have JavaScript representations that JavaScript is brought back to the browser and executed, and you can do lots of crazy things with that. But the moral of the story here is that with this display system, you can make your objects pretty. So that the things we're doing here with Matplotlib and SymPy to make SymPy automatically render to LaTeX and have that displayed in the browser, you too can add the necessary methods to have it things displayed in this way. To display, let's see here. Yeah, to display your objects, IPython has functions called display. And if you pass an object to display, you're going to get the representations of those. So you can request particular representations. The basic display method picks the richest representation that an object has. So how do you actually declare the representations? You create _repr_foo_ methods, where foo is HTML, PNG, SVG, LaTeX, JavaScript, and that method needs to simply return the raw data for that format. So if it's a PNG format, you return the raw PNG data. We take care of encoding that, taking it back to the browser, and it will be displayed automatically. There's nothing else you have to do other than declare these methods. There is another way of declaring display methods that I'm not going to have time to go into that allows you basically to say, for this class of objects, use this function. That's useful if you want to declare display logic for classes that you didn't write yourself. So that's also possible. So let's, what do you think? Should I stop?
Time-wise, we're about there. I was thinking you might want to show the YouTube video one, because it's not obvious that that would work.
Yeah, okay. Yeah, and I think I have internet access. That's in Notebook Tour, yes. So this is an example notebook that comes with the IPython notebook, and we have objects that wrap this logic for you that make it really easy to incorporate rich text. So if you import the SVG object from IPython core display and pass that, this SVG object has an underscore repr underscore SVG underscore method, and as long as you declare it, it magically pops up. This SVG class can also take URLs. We also have an image class that handles PNG, JPEG, those files. We also have an HTML class. So here, for example, is a video that's on the local file system, and we can pass it HTML code here. We're using, we're basically base64 encoding that video, putting it in a video tag, passing it to HTML, and that pops up and you can get an inline video. So we really want to emphasize this. You can do just about anything you would imagine wanting to do with the notebook and with this display system. And then I think, I'll show it from a different location.
Oh, you changed it.
I didn't think we would have network. So before we stop here, I want to show you what the development version of the notebook looks like, and I'll use that to show you this other example. So here's the new UI. It's a much more lightweight design. It has a standard menu-driven approach, and you can actually toggle the header and even toggle the toolbar. So it really gets out of your way, and we really like this new UI. And down here, so here is we actually, for fun, created a YouTube video tag that just includes the little HTML needed to display YouTube video. So you can run this and get, here's a talk of Fernando giving a talk about IPython. So you can create notebooks that interleave code, data, HTML, videos, just about anything you want. So you can tell we're having a blast with the notebook right now. It's some of the funnest stuff we've done ever, and there's a lot left to do. Multi-user support, being able to browse the file system. This feature that I mentioned, being able to have Python objects that declare JavaScript representations, is going to allow us to create basically JavaScript widgets that are able to interact with your Python code on the back end. There's a lot of potential for that, and a lot of interesting things. If you have interest in these things and working on IPython and the IPython notebook, please come and talk to us. We'll be around through most of PyCon. A lot of us will be here for the sprints. And with that, I think I'll stop. So
We'll take a 5-minute break, go to the bathroom, stretch your legs, and then we'll come back in 5 minutes and we'll do the third part of the tutorial where Min will present the interactive parallel computing facility that we also offer. So we hope you're not too tired. We know it's a lot of material, so refresh your brain for 5 minutes and come back ready for some rather intense stuff.
So moving on, now that we've done interactive Python locally in a shell, we've done interactive Python locally with a notebook, and you can actually run notebooks remotely. So you can do, with the kernel architecture we have that the notebook and Qt console use, presumably we'll come back. Hello. There we go. Once you have a mechanism for executing code remotely, and as far as the code is concerned, in the notebook, kernels are remote. They don't have to be on the same machine. They can be run anywhere. And once you have the machinery you need for remote execution, then the extra abstractions and code you need to run code in parallel is the next logical step. And IPython being written by scientists for doing interactive exploratory code, that a lot of what we need to do is in parallel or remote or with batch systems and on clusters and things. And so IPython has parallel computing machinery using 0MQ just like the notebook for doing that. So the general design of the architecture of the IPython cluster is that we have three or four basic building blocks. One is the hub, which is the big central process that kind of monitors everything, and I guess the starting point is really the IPython engine. So this is the kernel. You start out with the kernel that we use in the notebook. The IPython engine is a slightly modified version of that kernel. It starts with the same code, adds a few capabilities for changing connection directions and load balancing and things. And that's just a place where you execute code. It doesn't matter where it is. It's a process that listens for messages, and with those messages turns them into Python code and runs them. And then in the middle we have a collection of processes that we together call the IPython controller, which consists of the hub, which you can think of as kind of an Uber logger, that it sees when you try to run code on engines, the hub sees everything you do and stores it in a database, can be backed by MongoDB or SQLite, or can store things in memory. And so you can access results later, you can submit jobs, you can go away, and then come back a day or two later and say, okay, what jobs are done, and get those results. And the hub is what manages that. For talking directly to the engines, and this is when you're just running code, this is the hub is entirely out of the way, are these schedulers. So we have a collection of currently 4 schedulers for the client to communicate directly to the engines. And these are small, pure C functions, are written in Python, so they compile to C. They don't use any Python code. They don't grab the GIL ever. They're very lightweight, and they just manage multiplexing the client communication to the engine, so that you just have one connection point. You can just say, run code, and the schedulers will take care of sending those messages where they should go. And then every message you send to the engines, they also send to the hub. And then every message the engines send back to the clients, they also send to the hub. And all of this is somewhat magically facilitated by 0MQ and PyZMQ, which are 0MQ being a wonderful messaging library, and PyZMQ being the bindings for Python, maintained by Brian and myself. And what you actually use when you want to run code in parallel with IPython is a client object. You create a client. This is a lightweight manager for the various connections that you need to establish. And then to actually run code, you create views of your cluster that represent different models of execution, different subsets of engines, and that sort of thing. So getting started with the IPython cluster, since I'm not going to go into the fairly elaborate configuration options that you have available, but I will note that you can run, the IPython cluster will run with SGE, with PBS, with LSF. You can start your engines all in a single MPI universe, or you can start many groups of engines all in different MPI universes. You can start engines on just whatever machines you have in your house with SSH. It even works with Windows HPC, which Microsoft paid for us to do. But the simple case is I just want to run a couple engines locally, and that's what we're going to do for this example. And for that, you just do IP cluster start, and then the -n. Yep. Oh, that's way too small.
Way bigger.
Shell. I get you. How's that? Okay? I'm only going to run one command. So. This is all the shell I'm going to do. But so this is just start 4 engines locally. And it starts a controller and starts 4 engines and gets them all connected to each other. And then back in IPython, I just do from IPython import parallel and create a client object. So RC is my client object, and I'm going to start by doing some synchronous computation. So I just say block equals true. And a client has an IDs attribute. So that's just a list of the integer identifiers for the engines. Just for fun, I'll start another one. So I can add an engine. I just started an engine. And go back over here, check IDs. Now I got 5. And go back over here, kill the engine. Back over here, now I got 4 again. So engines can come and go over time, and it all keeps track of what you have available at any given point in time. And so to run some code, I just define a function. So here I'm just calling a function to multiply 2 objects. And so what does it look like to call this remotely? Well, you just turn a function with args and keyword args into calling apply with that function keyword args. And to get a view, so this says, give me engine 0. So if I ask for item 0 of the client, it gives me a view on engine 0. So I got engine 0, call apply, that just calls multiply remotely. And if we want to do that in parallel, just ask for a different set of engines and call it the same way. So I just multiplied by 5 by 6 on all of my engines. And Python has map, which just spreads out a call on various arguments. What does it look like to do map in parallel with IPython? Well, it looks exactly the same, but you use the method map instead of the function map. It does the exact same code. It just happens to load balance the work on your engines. And then when you're considering a new parallel computing tool, as there are many, one thing you want to consider is, how big do my tasks need to be that I'm breaking them up on this machine? And for that, I ran on a simple AWS cluster that I started up with Star Cluster. And this is just going to map little dummy tasks that don't do anything, that just wait a certain amount of time. So this is just going to run sleep for a certain amount of run 16 times 4 sleep for a period of time. And then this is just seeing how big do my tasks need to be that IPython is going to be out of my way. So and this just runs tasks from 1 millisecond to a second, and it's showing how much of my time am I spent doing the computation and how much of my time am I spending just in the overhead of using IPython. And it's just showing that I do reasonably well on my local machine, and then on AWS I ran, and you can see that if I get to the top of the graph, then IPython's out of the way. It basically doesn't count. There's no overhead that matters. And this is so if my tasks are 1 millisecond, then that's too small. That's IPython's not fast enough to handle that. But once you're up around, this is 1/10 of a second. Once your tasks take at least 1/10 of a second each, then IPython should be accounting for less than 1% or less than 2% of your total execution time. So that's the kind of size of task that you should be considering. And so the basic interface for working with IPython is you create your client, and then you have item access to create a view. So this I'm going to create a single engine direct view of engine 0. And then the rest of the interface is all about apply. Apply, you define a function. This is just a simple function I defined interactively. And then I create an array. And I call, this just gets me any number of norms on some array. And if I just call that function remotely, well, it ran, but I got a name error. The NumPy is not defined because I haven't imported NumPy on my engines. So the easiest way is just to execute import NumPy. But since part of the goal of this interface is to avoid code as strings, that we want to run code as much as possible and send code as text, have to type code in strings as little as we can. So we have a context manager called sync imports. And so if anything imported in that block will be imported locally and also on all the engines of that view. So with sync imports, I import NumPy, and this just imported NumPy on engine 0. And now I can call the function. Well, I can call the same function. And now it ran without a name error because it was imported. Let's say I have, this is 12. So I have a script that defines a function, defines a variable. Just like in IPython, you can run a script to get to run that code in your local namespace. You can run a script to run that code remotely. And then I can execute some code, so b equals my square a. And now I can get a. A is 5, b is 25. So I just sent the script over the wire, executed it, then executed a line of code, and now I can pull the variables back. Working with the engine namespace, this should be familiar for Python developers, that the persistent namespace is just globals. When you define a function and you call that function, call that function remotely, the global namespace is persistent for the lifetime of the engine. So in this case, I have a defined from my previous code, and I define a function locally that gets a as a global variable and then adds to it. So this is a function that increments a remotely. And I just get a, and then I call increment a, and then I get a again, and you can see that my new value is larger than the first, and I can keep running it over and over again, and it keeps incrementing a. And just like normal, if you're only reading from the global namespace, you don't have to declare global variables. I can multiply by a, and since a is in the globals, it pulls it out of there. And I can multiply anything by a. Sometimes, if you're actually moving information around, you don't want to do that every time. And what we have a little helper for that called a reference object. And all this is just something that if I call apply with a function and a reference, then what happens remotely is that gets the actual object. So if I call is it a with a reference to a, that's actually going to call remotely is it a on a. So a reference to a comes back as will be a. So sometimes you want to send data from your client to your engines, and the basic methods for that are push and pull. Push just takes a dictionary and just updates the global namespace with those keys, and pull just gets one or more names, and you can get those back as either the value itself, or if you get more than one, you get a list. Since a namespace in Python, a namespace is a dictionary, a view presents a dictionary interface. If you set key a equals range 5, then this just calls push, and then get item calls pull, and get and update work just like you'd expect. So if you treat a view as a dictionary, it's basically a remote dictionary. Often you don't actually want for everything to finish. You want to submit work and submit more work and keep submitting work, and then only wait when you're done submitting code, or never. You can, if you're not interested in the results of your computation, if you write to the file system, you don't need to wait for the results. So for this, we have an attribute called block, and if you set block equal false, then what you get from every method on a view, you get an async result object, and this async result object presents a superset of the interface in multiprocessing.pool.async result. So if you've used multiprocessing for asynchronous computation, you should be familiar with what this does. So now that I've set block equals false, and I call apply, I get an async result object. I can ask if it's ready, and then I can call get with a timeout. So it wasn't ready because it was still sleeping for 10 seconds. I gave it a timeout of 1, so it's waited up to 1 second, and then raised the timeout error because it wasn't done yet. But then if I call get with no timeout, it will block until that execution is done. And then get, and then we'll return the actual result of the computation. And for convenience, there's a _sync and _async, which set block for an individual call, so you don't have to rely on the attribute. So apply sync, and I can call apply async, which didn't wait, and then I can wait on the result of that. So that's the basic interface for remote execution, but we were only working on one engine. So the first mode for working in parallel is to create a direct view with more than one engine. And in this, you treat the IDs, you treat the client as a list, and you can slice the client, and it just slices the IDs list. So I can get engine 0 for a single engine view, just pass colon for give me every engine. I can slice it to give me the even engines, and slice it to give me the odd engines. Anything you can do with a list, you can do with the client. And so these are my various views, and I'm just getting the process ID of the various engines. And a direct view of multiple engines has the same interface as a direct view of one, but you get lists. So if I set A equals 5 on a view of all my engines, I set A equals 5 on all my engines. If I ask for A, then I get A from everywhere. So I get 5 or 4 versions of A here. Sometimes you have, you want to just break up your work. You've got, say, a list of arguments or something, or a list of data files you want to do work on. You can distribute that with scatter. Scatter just does a simple partition of an iterable. It can be a list, a NumPy array. And so this shows that I just sent 4 elements of the list to each engine. And then the inverse of scatter is, of course, gather, and then that gets me a flat list. And I can, for instance, create a sum on the partial list, and I gather, and I get the partial sums. And then I could do, with this, you can do simple MapReduce type operations. Common for you want engines to, if you want your code to know which engine it's running on, a common operation is to scatter the IDs, the IDs list of the client, and you want everybody to have their ID as a variable, but you don't want them to be a list of length 1. That's not very helpful. So if you specify flatten equals true, then any engine that would get one item of the list will actually get that unpacked and get the item itself rather than a list of length 1. And scatter and gather also works with NumPy arrays. So here's a couple NumPy arrays, which are just transpose shape. One's 4 by 16, one's 16 by 4, and I can scatter both of those and see what's on engine 0. For the first one, the engine 0 got a 4 by 4, and for the second one, the engine 0 got a 1 by 16. So they just got the first. Scatter only works on for NumPy arrays works on one axis, works on the first axis or the last axis. So with this, you can write an incredibly terrible matrix multiply. So this is just computing the dot. For breaking up the computation of the dot product, I send B everywhere. So every engine has the entirety of B. And then I just distribute A. And then I compute the dot product on each engine, the dot product of B and the subarray of A, and that gives me the subarray of C. And then I can just gather C. So this is just a distributed dot product. And that shows that performing a distributed dot product gets the exact same result as performing that locally. Obviously, if you were doing real work, you wouldn't want to do anything actually this way. It's just showing that with simple building blocks, you can do simple things, and that's part of the goal. That simple things should still be simple, which is often not true of parallel computing tools. So with simple map, what does map look like? Well, map looks like the exact same thing, but a method instead of a function. So performing the same, just passing a lambda and a list. This basically did behind the scenes, did a scatter, apply, and gather of the results. So when you do map with the direct view, you get one task. You submitted basically one request to each engine, no matter how big the list. It always submits one request to each engine. So I've got 4 engines. So no matter how big my list is, I'm always sending. In this case, I'm sending 800 elements of the list, calling map remotely, and then getting 800 elements back. And this will be relevant when we get on to the next part. So that's the basics of multiplexed execution with IPython. That if you set up your engines, yeah.
Kind of related question. If I would like to connect it to R, for example, in different engines,
Yeah.
would that kind of move to R with Python to run on the engines? Or, I mean, is it something?
Yeah, so the question is, talking to R, so the IPython engines, when you're doing this, you're sending actually Python code. So there's 2 ways. So execute sends code as strings, and with that sort of subset of the interface, you could actually talk to a process in any language that speaks our protocol. That would require replacing a significant amount of machinery, but in general, it's actually sending code, Python code objects. And with that, if you want to call R from your engine, if you have your Python to R interface running in your engine, then you can do that, of course. And anything you can do locally, you can do remotely, right? But sometimes you don't actually care where your code runs. You just want it to run somewhere. Get it done. Say, I have this bunch of work. Just run it in some order. Let it go. I just want this code to be run. You decide where to run it. You decide who's idle, who's available to do work. And for that, we have a load balance view. So to create a load balance view, you just call the load balance view method. And this gives us a load balance view. In this case, by default, load balance view is lazily evaluates to all engines. That is to say that it doesn't care where it runs. So if you submit code to a load balance view and then bring up an engine, that engine is considered an appropriate target for the code. You can restrict load balance views to subsets of engines. And this will submit work that will be load balanced, but it will only be load balanced across engines 1 and 2. So again, I'm going to create a single engine view and then perform a simple compute the norm remotely. And the load balance view looks like a single engine. It does the exact same thing. It provides the same interface as a direct view of one engine. However, unlike the direct view always runs on engine 0. So run that over and over again, and it always gets the same result because it's always happening in the same place. I can run the same code on my load balance view, and while the results look the same, it actually keeps executing in a different place. But you can treat it as you can use a load balance view just like a single engine view, you just don't actually know who it is. And for that reason, the load balance view does not provide the namespace access, because load balancing namespace access would be weird. If every time you get A, you get a different person's A, and you don't know who it was, then that's not especially useful. So we don't provide that interface on the load balance view. Load balance view has map, just like the direct view, and it results in the same code. But unlike the direct view, it doesn't chunk it into one task per engine. It chunks it into one task, by default, chunks into one task per item. So for this, if I did the range 3200, it would by default do 3200 tasks. And since that takes significantly less than 1 millisecond to run, that wouldn't make any sense with this particular sample. But map results, so now I can do asynchronous submission of a map, and this gives me a subclass of async result called an async map result. And these are iterable. So if you iterate through an async result, then you actually iterate through the results of that computation as they come. So you can iterate through an async result immediately, and you'll get the items. You'll get the items as they come. And this is showing execution. This is sleeping for. So I've scattered ID, right? So everybody has their own ID, and I'm sleeping for my ID number of seconds. So I slept no time on engine 0, engine 1, engine 3, and let's not do that. You can see that the results come as they finish. And then we can submit a bunch of tasks in increasing magnitude, and these will run load balanced, and this is going to show that every task is actually, they're being assigned, each task ends up on a different engine, right? And often, you want to distribute your work like that, but it makes more sense that each task shouldn't be one, each element in the map shouldn't be one task. Maybe 4 elements in the map should be a task, or 10 elements, or 100 elements. And for that, we've got a chunk size keyword argument in map. And what that does is it tells you how much should be in any group. And so when we run with chunk size equals 4, each engine's getting 4 at a time. So an example of taking some blanking on the word, the easily parallelizable action. You just want to call a function on, you have a number of arguments, and you just want to call it over and over again with the different combinations of arguments. So this is just computing the area of a bunch of rectangles, and you've got a number of widths, and you've got a number of heights, and you want to compute the area of all of those rectangles. So this is just a nested for loop, compute the areas. And so how do I parallelize a nested for loop? Well, this is from a Stack Overflow question a week or two ago. And the main thing is you just want to turn your two nested lists into two lists that kind of have the right shape that you'd get with the nested loop. And for that, two built-in tools in Python of itertools.product and zip help. And I'm going to use loadpy here because I've already written it. Yeah. Let's go big, nice and big. All right, so itertools.product can turn two lists into a list of tuples. So this is width and height for each call in the nested loop. And a fun trick for turning a list of pairs into a pair of lists is called zip star on that object. And then we've got all heights and all widths as they would have appeared in the nested for loop. And this little trick works with arbitrary levels of nesting for loops to turn them into the arguments you need to pass to map. And so I just called once, given my widths and heights, I created the longer lists that have that are the right length for the nested iteration, and then I call map async. So I've got my async result object. So AR's async map result with area, and then AR.get is the same, right? Now I'm going to do some more interactive use, starting in Qt console. And we'll make the font really huge. So I've still got my client and my load balanced view. And now we're going to look at interactive exceptions. So when you're doing stuff interactively, you want exceptions to raise. So if I do, say, so this is obviously going to raise. So just call 1/0 remotely. For that, we get a remote error, which has the traceback of the original, which we also saw with the import error, the name error on NumPy. We also have various decorators for defining functions that can be called remotely. Oops. So I can do mul a. Oh. Right, so that's a scattered list. So I just multiplied a bunch of lists. Let's see. There, now they're IDs. So du. And now if I call mul. So this is a function with the decorator, the remote decorator, and this can take a block keyword args. So if I call block equals false, then I get an async result object. Right? Don't want to apply a number. That's going to sleep 10 and then raise an error. Right, so AR is an async result object. AR.ready. Wait for 1 second. And this also works with exceptions. Right, this isn't going to work properly. But if AR.ready, but AR.successful is false because that actually raised an exception. When I call get, I actually raise the exception. So whenever you ask for an object, whenever you ask for a result, if computing that result actually raised an exception, then an exception is going to raise locally. To summarize, we've got IPython provides simple interactive tools for doing remote computation. You can load balance, you can multiplex, you can do synchronous, you can do asynchronous. We've got lots of we've got lots of more subtle integration with various other tools. Magics for parallel execution, and working with the database that the hub stores all the results in. You can work with that to get results at a later time. You can handle engine seg faulting, resubmit tasks. You can instruct the scheduler to resubmit tasks automatically up to a number of times. We have functional dependencies. We have graph dependencies. You can instructs tasks to run after any subset of other tasks. Basically, we support an awful lot of things that we're not talking about here, and you can see all of that in the parallel documentation. And the one last thing I'll go over is a view of what the implementation looks like. Is the connection diagram of the 0MQ sockets of the IPython cluster. This is what the IPython cluster looks like as far as network connections. So in here you have what we call the controller, and each one of these is a PyZMQ monitored queue device. So these are the little C functions that have 3 sockets, and the socket types depend on what those are for. So that this is if you're familiar with 0MQ, the dealer is a load balancing socket. So you just plug in a dealer and it load balances. And then the router lets you do multiplex execution because the router does routing by identity. And then standard out and standard error are piped up in the same way, just the other direction. And then control messages get to basically jump ahead of the line. So you can say, I submitted a bunch of work, but I realized there was a typo. Don't actually do it. You can abort tasks via this control queue, and those jump to the head of the line. And everything comes into the hub, which is, as I said, kind of an Uber logger that gets everything, sees everything, logs everything, in order to be able to get tasks over and over again, get tasks from previous execution. And this also monitors the state. This is the hub is the process that allows the IDs property of the client to always be up to date, because they get notified every time an engine comes, every time an engine dies, and that's how you're able to handle segfaulting engines, handle scaling your work by just saying, all right, now I have a lot of work to do. I can just spin up some more engines in the cloud and just connect them to your controller, and it just works. And these are up top are the client connections, and these are the connections involved in the engine. And that's the IPython.parallel machinery. Yeah.
So you showed how you were pushing state to the engines.
Yep.
For running tasks, and you could scatter like their IDs. But if an engine segfaults,
Mm-hmm.
and or say you add another engine,
Mm-hmm.
either way. So some engine is coming up, and it's coming up in a naive state. How does it become equal to its peers that have had that initialization done?
So that's going to be.
You should repeat the question.
Oh, yeah. So the question is, how do you handle engines joining your cluster? And if you have some initialization code that should be run before using that engine, right? So there's 2 ways to do that. If you have really basic initialization that all your engines should always do, the engines actually can take a startup script that, and you actually you wouldn't use the interactive machinery for initializing engines. You can actually initialize engines with any amount of running scripts before registering themselves with the cluster. And so if you've got imports or whatever for that. The other is that if your engines are a significant function of time, you can define dependencies in the tasks themselves that actually ensure that things happen and can trigger. So there's a require decorator that will basically perform imports if necessary. So you can say require NumPy, and then call a function that assumes NumPy is in the namespace, and then it will be there even if it wasn't before. So let's start another. Was it 5? What did I just do? Yeah. Okay. So if I've got that, so E, Right, NumPy is not defined, but if I do right, so you can call require decorator, it gives you imports and things. Yeah.
Well, it's sort of a related question. How much control do you have over the workers? Like, let's say you started some operation, but the worker just ran away from you. Let's say it ran into C code and it's like stopping.
So currently we don't have, so we do intend to insert a little nanny adjacent to the, so basically you saw that control channel of messages. The plan is to insert a little nanny that gets the control messages and can say, all right, interrupt, restart, kill, just like we can do with the notebook, but that's not in place right now. So basically if you, you can say, like I did, sleep all day, or do something that's going to seg fault. The only thing you can do, all your actions are evaluated sort of between tasks. So right now there isn't a mechanism for interrupting the engine, but it isn't hard to do that, and we intend to.
So those 4 engines that you started are all on your system. Let's say everybody in this room started up several engines. And
Yeah.
you wanted to kick off work to them. How would you discover them, get them into your namespace, discover them, and then kick off tasks?
So we have these connection files. So there's a connection file. How do you share the connection information for engines on different machines? And the way you do that is that when I started the controller, it created a connection file. Let's use my visible terminal. And then there's IPython has a little security directory, and then it puts the information necessary to connect to a controller in a little JSON file. So, and there's one for clients and one for engines. I'll just use more. And right now, that just has the registration URL, a key used for authentication. So all messages are actually signed so that you don't have people with the URL of your controller don't actually have the ability to run code because messages are actually signed. And then we also will help out with SSH tunnels. You can put in IPython will actually launch SSH tunnels for you if need be. And then the location is used for disambiguating URLs. So just like the notebook can listen on all interfaces, if I tell the controller to listen on all interfaces, I need to know where the controller is to know if I need to connect to a remote IP or localhost. And then, so this is the file that you distribute, and then you tell your engines where that file is. And if you're on a shared file system, then there's not much you need to do other than tell the controller, just like everything else, the controller listens on localhost only by default. All you need to do is tell your controller to listen on an IP that's visible to the rest of your cluster. And if you're on a shared file system, that's the only thing you need to do. Just bring up engines with the same profile, and they'll connect. And the same with clients. And you can do that remotely, across, if you want, you can do that across the internet, and the recommended way to do that is with an SSH tunnel or VPN. Yeah.
I remember multiprocessing had problems pickling like different objects. If you instantiated something, you defined it interactively. How are you sending code around? Do you get around this problem?
We have one little trick that we do to help to make some things more pickleable, make functions more pickleable specifically. But that's a tiny, well-known Python trick for making code objects pickleable, I think. We will, if you do have closures, it will block. The question was about dealing with issues involved with pickle. And most things do need to be pickleable. So you can run into issues with Pickle for some interactively defined things. But for the most part, we found that we don't run into too many problems. But you'd run into all the normal problems with Pickle that you expect. Yeah?
So in your experience, how robust is all of this? Or maybe put another way, how often do you have to just reset the universe?
How often do I have to reset the universe? So the standard model is that an IPython cluster lasts for the lifetime of a simulation or a workload. So you, rather than like with PBS, where you start it once and it runs for the lifetime of your hardware, we expect most IPython clusters to run for closer to the order of hours, days, or maybe a week or two. And I haven't had too much need for killing it and restarting it. I know some people have, and right now with the current code, the controller is a single point of failure. If your controller goes down, then your engines are useless. There's a currently outstanding pull request that allows the controller to die and come back, and the engines continue to function.
Yeah, I guess the reason I ask is that having done parallel computing, it seems like
So it's very tolerant.
they tend to go wrong really big time.
So it is fairly tolerant of engines going horribly wrong. So engines segfault all over the place, and the load balancer says, oh, that engine's gone, I'll resubmit its work somewhere else. For engines, it's very tolerant of engines just exploding all over the place. For the controller, that's not true. Yeah? So right now the engines are pure Python. They're not IPython, so they don't perform the little translations of. But we do actually have plans to be able to launch IPython in an engine, so that you can connect a Qt console to an engine and interact with that.
It's got to be done by May, so.
Yeah.
Our deliverable is in May for the DoD.
Yeah. So that will happen by May. We are obligated by funding to finish that by May.
What's the recommended procedure for shutting down a cluster when you're done with it?
The recommended procedure for shutting down a cluster. rc.shutdown. Oops. Oh, maybe it's hub. So by default, shutdown shuts down all your engines. Yeah. And if I peek at the cluster process, yep. So this process was running, waiting for the cluster to exit, and I just called shutdown. It brought down the engines, and it brought down the controller. And you can shut down, with the same interface, you can shut down individual engines, one at a time.
So when you call shutdown, what if there are some engines which have some messages that are still pending in its message queue that it's still wanting to work on?
So it's basically, it's trusting you. So if you say shutdown, it believes you mean it, and it believes you mean it right now. So if it's got, what it will do, since that is a standard message, it is not forceful on the engine, it gets that in the control queue and will finish its current computation and then exit cleanly. But it will not compute anything current outstanding in its queue.
Is there a polite shutdown saying shutdown after everything has gone through?
The way I would do that is,
Repeat the question.
so a polite way, a polite shutdown for finish work and then shut down. What I would do that is from a client script, because you can wait on work, whether you submitted it or not. You can say, wait for the find out what's running, wait for it, and then submit shutdown. So I would basically do polite shutdown at the client level. Okay. Yeah, so star cluster, which I use for my AWS test, star cluster who here is familiar with star cluster? not enough people. So Star Cluster is not at this URL. There it is. So Star Cluster is just a little Python toolkit for working with Python on AWS easy. And it really does make it unbelievably easy to bring up clusters, to bring down clusters. And they have an IPython plugin that I wrote that is bundled with Star Cluster. Justin cleaned it up and made it better than I had it, but that makes it really, really easy to start to bring up IPython, the IPython notebook, or the IPython cluster on AWS instances. And yeah. Plugins. Yeah, so the plugins they have. And and Star Cluster, they maintain AMIs that the Amazon machine instances that have that have kind of a basic scientific computing in Python environment. They have Python, they have NumPy, they have SciPy. I think they have IPython. They have, I think, pandas now, probably. I don't know. Everybody should have pandas. Yeah, and the IPython cluster just lets you. And the way this works is because the Star Cluster sets up with SGE, and so the IPython cluster actually launches engines with SGE on the AWS cluster. And you basically need 3 lines of config, and it handles opening it on the right ports, and it brings the JSON file. The plugin brings the JSON file from the cluster to your local machine, so you can just connect with the file and just run code on AWS from your laptop. Yeah, so if you do AWS and Python, you should be doing it with Star Cluster. If you're doing it with anything else, you're doing it wrong. Okay. All set. Yep.
So we're basically coming to the end of the session. We're supposed to stop at 12:30, and we'll try to keep it on time so that everybody can get lunch. It's been a long 3 hours. Are there any last-minute questions on the whole thing that we can answer, either Brian or Min or myself, that we can answer? And I think we have time for 1 or 2 sort of generic questions. Yes?
Probably a really good place to find a good tutorial on IPython online.
So that hopefully would be our documentation, one would want to believe. So if you go to ipython.org, which is our website, there is incredibly documentation for the project. And so we tried to keep documentation available for all the old versions is available there. And the current development version, you guys have 0.12, the docs haven't changed too much. There is documentation here, and it's not perhaps organized in the best possible way. I would like to have an organization of our docs that was a little bit more like what Star Cluster uses, which is sort of more along the lines of the standard Python docs and broken into a tutorial and more API docs. But it is, our docs could be improved, but there is a lot of documentation, and it's separated mainly into using the pure interactive features. So this section of the docs has both the terminal use, the Qt console, and the notebook, and then a section on the parallel computing machinery, which obviously brings in some new abstractions. We would definitely be happy to take feedback on it. If it's confusing, if it's not what you're looking for, let us know and we'll try to improve it. And this is an area where actually new users could help us a lot. Often a new user can improve the docs because their vision as a new person coming to the project actually lets them organize the ideas better than those who already know it so well that they don't really realize that it's confusing. Yes, David?
Do you know if anybody's used IPython notebook with like mapping or GIS stuff?
Not that I know of. We released it, the actual release of the notebook was only 2 months ago. So this is the official release. It was sort of out in the wild. We announced it, we merged it into Gitmaster for the EuroSciPy conference in August of last year where I delivered a talk. And that's when we announced it. So some people were using it from Gitmaster since August, but the official release was right before Christmas of last year. So there hasn't been too much use in the wild that we know of. We would love to hear. And I guess this brings up an important point. If you do use IPython, one thing that we would appreciate, especially if you use it on an academic project, is that you keep this little citation link mindful. All that we ask for, this is currently, unfortunately, the only academic reference that we have is one where only Brian and myself are authors. We plan on writing soon something that credits the whole team. But it's important for us that you credit academically if you use these tools because we do search funding from the national funding agencies. And it's much harder to justify that you're an important project if nobody actually cites what you've done, believe it or not. So if you know of any use in such a field, please let us know. Yes?
I'm interested to know about the embedding capabilities of IPython.
The embedding. Yes, so unfortunately, we ran out of time for that. How many people are curious about the embedding capabilities? And I can show very, very briefly. Okay, I'm going to show very, very quickly just one example. I'm not going to. In our examples directory, there are examples called ipkernel Qt app and ipkernel WX app, and I'm simply going to show you what they do. These ship with our docs. You can study the code. What this does is opens a very simple little Qt application that has a namespace, that has a variable which is a counter, and which can open a Qt console pointed to its own namespace. So in here, for example, I can click on the namespace button and that executes code in the console. I can increment this counter, print the namespace again. Here, I can set this variable, I can set it to 100. Oops. If I keep incrementing it and I print again, now it's 102. So the point is this shows you with a very teeny toy application how this could be your GUI code, right, which has its own variables and does whatever it is that you're doing, and you can create a kernel, an IPython kernel inside of it, which listens with the standard protocols, and then you can connect an interactive console to it. And this can be done with Qt, or it can also be done with WX. So the same exact code runs as a WX application. Well, this is my old console. And now this is a WX application, which can still use the Qt console because the WX code and the Qt code are running in separate processes, right? So these are two ways of embedding a kernel in your own code and then using the Qt console widget to talk to your namespace. But unfortunately, because we're running out of time, if you have any more questions on the embedding topic, just come to me over lunch and I'll be happy to look into it in more detail. So I think questions-wise, that's probably the time we had. We'd be happy to chat with you over lunch. A bit of a few final notes. We'd like to thank Stuart Williams and the organizing team. They did a terrific job putting the tutorials together. The video team, it's awesome that all of this tutorial, these 3 hours, will be put up online shortly. I really want to thank Paul Ivanov and BrianE James. Paul is a grad student in neuroscience, and BrianE is a postdoc in astronomy at UC Berkeley. Both of them use Python tools to do extremely interesting research in their fields, and they were your TAs for the day, and they were kind enough to just volunteer and come down here to help us out with the crowd, and obviously you, the audience, for coming and sticking with us for 3 hours. The few last-minute things, we had 5 USB sticks, 4 black ones and a silver one that were passed around. If one of those is lying somewhere near you, we'd appreciate it if you pass it back as well as the CDs. And then Stuart asked me to make sure that you please go to this URL and take a short survey on providing feedback on the tutorials. The URL is also pasted on that sheet of paper by the door. You can also, I don't know if you want to just take a picture of it with your smartphone so that you can give feedback to the conference organizers on the tutorials. And in our presentations page, I've just uploaded, that's the URL in our docs to our presentations page, which you will always find from our homepage. There's a link always there to talks and presentations. I've just put up the slides, the PDF slides that I used in the intro section and the slides for the notebook presentation that Brian gave, because those were the only two things that were not in the materials we gave you. Everything else was on all of the notebooks and everything else we used was on the USB sticks and CDs that you had. All of Min's notebooks are online. I guess we can just put up a link afterwards to the GitHub repo where they are online. So I think that kind of closes it. It's 12:29 on my computer, so let's try to keep it on time so everybody can have lunch. Thank you very much.